traîne un peu, vous attendez, tout le monde raccroche les wagons. C'est qu'hier, j'ai eu 2 heures pour tout faire, c'était compliqué. Du coup, j'ai fait que le début. C'est dur de suivre tout le monde, mais là, vous avez le temps. Il est bien ce petit ventilateur, n'empêche. Générique? Comment ça, le générique est pas parti? Ok.
Et mon micro, il marche. 1, 2, check, 1, 2.
Ouais. Okay, so we are back in Gresham School. We have internet. That's a good point for worldwide school. So welcome to the Python day of the GPU week, so the day 6 of the Gresham School. So we'll do some Python on GPU, so with JAX, with cunumerics, with a lot of stuff. I don't want to spoil the full day. So we'll start with Jean-Marc, then with Alice. So Jean-Marc, it's up to you.
Thank you, Pierre. So this morning I speak about CuPy, and the last course is on GitLab. So I put the link in the Discord in Grayscale School 2026. So this link. So CuPy. So the goal of the project is to provide Python user GPU accelerator compatibility with without the in-depth knowledge of underlying GPU technology. The CuPy teams focus on provide complete Numpy and CPy API coverage to become a full drop-in replacement, as well as advances the CUDA feature to maximize the performance, and provide a mature and quality library as a fundamental package for all projects needed acceleration from a lab environment and to a large-scale cluster. So CuPy use CUDA toolkits library, include QBlast, QRound, QSolver, QSparse, QE50, and so on. They also support GPU AMD as experimental support for WorkM, and with also some limitation like features specific to CUDA. So here we have the speed up of QP over NumPy for different kind of calculation. The speed up scale is a logarithm. So you have two magnitudes between the max and min. And you have two kinds of array, a small array and a large array. 800 megabyte and 8 megabyte. So the speed up depends of the size of data. Small data result in less gain. And you have two types of processing. Element-wise operation bring the best gain, like this. and you can be a factor of 10 between the speed up of the complex operation and the element-wise operation. So in this operation, the algorithm needs to access to all data, and there are memory issue to process the algorithm. For example, matrix multiplication. So the speed up is only 10. And for element-wise, the speed up is 200. Memory and array. So you have two kinds of array, an array on device and array on the host. So device is always designate a GPU and host a CPU. Whenever we are moved around an architecture where a CPU and a GPU share memory, such as the new NVIDIA Grace Hopper superchips. So host memory and Numpy array. So Numpy array is obviously stored in a host memory linked to the CPU, and CUPI array return an array stored in device memory. All array allocation as done on the current device by default is ID 0. So here's a sample array allocation on GPU. And you can ask where is the memory with attribute device, and return the device where. Transfer, data transfer. So to transfer data between host to device, H2D. It's very simple. You only create a CUPI array with parameter and a Numpy array, and the data are moved, copied to the host, to the device array. For device to host, you have a method get with the array class in GPU. So you create a memory in a GPU with a CUPI array, and to get on CPU, you apply only the method get of the array, as the transfer is performed. You can also define a new Numpy array and use the method as Numpy, and the parameters is GPU array, and the transfer is performed too. Cost of the transfer. So note the converting between a CUPI array and Numpy array incur data transfer between the host and the GPU device, which is costly in terms of performance. Small and frequent memory transfer penalize performance. Good usage, good memory usage and transfer are the key to a good GPU performance. So the first tip to improve the transfer is the Pinot memory. Pinot memory, as also known as page locker memory, provide significant performance benefits to host device transfer. Pioneer memory allocation is done by a QP-specific function. And for transfer device to host or host to device, you use memcopy functions like in C, is used rather than the get method of the array on GPU. So the allocation of the Pioneer memory is based on an allocator function provided by QP. So it's QP CUDA alloc Pioneer memory and the size of the array. And we need to init your Numpy array with the return value. So for example, you want 150 image in a float 32. You call the alloc Pioneer memory with the number of the image and the size of the float and return address memory. And after you can initialize your Numpy array this allocation. And you must define the type. You can also use a user-friendly function provided by QPyX. There are methods like Numpy allocation array. And you have underscore Pioneer at the end of the method. So you retrieve all classical methods of Numpy array: empty, 0, empty like, 0 like. So it's easy to use Pioneer memory with this function. So an example of transfer memory with Pioneer memory. So you must use a memcopy function. So the memcopy is provided by CUDA, QP, in a CUDA library, runtime, and memcopy. And the first argument is destination, the second is the source, size, and the kind of transfer. This parameter defines host to device or device to host. So here it's a copy device to host. When you use a stream, we'll see a stream later. You have an asynchronous version of memcopy with the same parameter, but the last you must specify the stream associated to the transfer. So,
when would you use runtime.memcopy as opposed to get and as array?
The method get don't deal with Pioneer memory.
Okay.
Because in fact, at the QP level, the library can go to the AMD GPU and NVIDIA, and this kind of memory is only available for CUDA part. So QP provide a clone of Numpy. So the first object important is array. There are some difference between a QP array and Numpy array. They are very similar. The difference for the difference we have same attribute and more. So in a QP version you have a device attribute. Some method some methods are not available, like a resize, and you have also the get method to return a NumPy array. There are some difference with slicing feature. CuPy never return an index error of integer array indexing. I have an example below. CuPy array support broadcasting, and date type is the same, exception for the float 128 is not available. And how distinguish Numpy array from QP array? Maybe sometimes in code you forget the origin of the array. So you have a method type to know where is come from the array. So here you have the difference between NumPy array and QP array for the fancy indexing. So here I define an array with 3 elements. And I use a fancy indexing, and the index 3 is not available. So Numpy return an index error. And the same thing for QP, they return no error. So no check for the fancy indexing. Now the routines. So you have a table, comparison table between Numpy and QP. So as you can see, is very complete. I see recently in CP documentation in API reference, for example, blah blah. Signal. In the CP documentation, there are now a table with the portability in a different library like QP, PyTorch, JAX, Dask, to see the curvature of the function done by these libraries. And another difference QP only provide ND array. There are no record array or structured array in QPy. You have only ND array. So no array with a column name. Okay, it's a simple ND array. So the first processing. You define a function with the QP method. And if you call a QP method, the processing is done on the GPU automatically. You don't have to specify anything. The memory, here you allocate memory with QP function. So the memory is automatically on GPU. And if you apply a QP function, the processing is performed on GPU. So it's very easy. QP provides some benchmark tools. In a profiler library. So to use a benchmark, you call a benchmark function with the name of the function, the argument to the function, and the number of repeats you want. And the benchmark return two timing, one for GPU and one for GPU. Yes.
Yes. Could you please go full screen so we can, when you scroll down, we don't lose the previous part of what you were explaining? Just so we can see more at once. If you press like F11 or something.
Tu veux que je revienne
Ah non, est-ce que vous pouvez mettre en F11 pour qu'on voit plus à la fois sur l'écran?
D'accord, oui.
Merci beaucoup.
Donc, it provides two timing, one for GPU and one for GPU. So the timing for the simple function square root take 400 microseconds. And if I perform the same function with Numpy, the time int return 4 milliseconds, so the speed up is 10 for GPU. And we compare at the end, the results are the same. So here you see I have the result on the GPU and apply the method get to transfer on the CPU to compare with Numpy function all close. So here you have a transfer memory. QPy provide also CP function. And you have a table of availability of function of CP function. So it's less coverage than Numpy. There are some blank. There are some functions that are not here in linear algebra. So the best coverage is for multidimensional image processing, and the worst coverage of the CPy libraries is for statistical function. So the important point said. QP arrays are very similar to Numpy arrays. Conversion between a QP and Numpy array cause a physical transfer between GPU and CPU. And the QP version of Numpy and CPy function are processed on GPU. Now we will see the user-defined kernel. There are different kind of kernel for user. Here you have the list. Element-wise, reduction kernel, row kernel, row module, fuse. I present only 3 in this presentation. So row kernel, it's like a CUDA. The row kernel object allow you to call a kernel with a CUDA large kernel interface. In other words, you have control over grind size, block size, shared memory size, and stream. Here an example of the row kernel. So as we can see, it's a string. Is defined as a string, and in string is a C code, and the last parameters is the name of the kernel. I think. So the signature of the kernel is defined here. And when you call the row kernel, you must choose a number of grind, number of block, and parameter your array. The second kernel is a JIT row kernel. It's similar to a row kernel, but with Python syntax. So you already have the control over grind size, block size, and so on. So you define this kernel with a decorator, JIT row kernel. So in the example, you perform a copy element-wise. So recognize the typical line for CUDA kernel with the index of block, the dimension of the block, and the thread index. So last kernel is a fuse kernel. It's a decorator, and you can use element-wise in the kernel and reduction kernel. In this form, it's like a Python code. And as we can see, the parameter grind block has disappeared. So you don't have the control on this parameter. There are some limitations. All reduction functions is not available, and some routine is not available too, like math multiplication or reshape. And as I said, you don't have the control over grid and block size. So it's some simple kernel. Sorry. So now an introduction to the concurrent processing. So parallel execution of different processes is possible with CUDA GPU. This is the concept of stream, which is equivalent to a thread on a GPU. Remember that a thread has a different meaning in a GPU domain. Stream creation usage is straightforward with CuPy. Here you have an example. Create two streams, A, B, execute in parallel, and you can merge the result at the end. So here to define a stream, it's you call the QP library a CUDA stream with parameter no blocking. You create memory on GPU, and to start the stream, you just use the keyword with stream, and all lines here will perform in the stream. So actually it's empty, but if you ask computation, the computation will perform in stream A. And the program is not blocked to this processing. They go directly to stream B and execute stream B. If you want to merge the result of A and B, you must wait the end of the both stream. So we have a keyword method synchronize to wait for A, the end of the processing A, and the end of the processing B. And with the two streams is synchronized, you can merge the result in the two buffers associated to the stream. So the computation was performed in parallel. So there are two constraints to execute a stream in parallel. The GPU has enough resources for both processes. And process should not be too short. Else it's not efficiency to start a stream for a few calculations. AEB can do different things. Typical example on a GPU is a memory transfer and kernel execution using in the double buffer transfer. So an example of a stream is it's a double buffer transfer. So in this example, you can compute and transfer in the same time. And if this transfer is you can compute and transfer in the same time. So the stream associated to the computation will will use a buffer associated to the both stream transfer. And they now wait that the transfer is n to process. So here you have an example. So I define a size of array. I create 2 buffers in a GPU. I create 2 streams for transfer called D2H, device to host. I create data input. And the thread computation is performed in a default stream. You have always a default stream. For example, for the first computation, the very basic computation, the processing is performed in a stream default. You don't have to define the stream. The stream default is always defined. So in this calculation, you use stream default for the computation and 2 streams for the transfer. So if you want to compute, the memory must be available. So the memory is associated to the stream. So you compute your processing, and in stream you do the transfer. You return at the beginning of the loop. And if so you use index. We switch between 1, 2, 1, 0, 1, 0, 1, 0, 1. It's the index of the stream. And if the stream of transfer is always transfer, you can stop the processing. So you do the processing only if you have a buffer available. So the first and second call, it's available, and for the first, you must ask for synchronize to know if the buffer is available. So you have a comparison with and without double transfer. I create a little benchmark on NVIDIA A100. And in fact, this version is with classical memory. And the exercise has to use Pinel memory. And the benchmark is a difference between classical memory and Pine memory. So for this example, the speed up with Pine memory is 3. Maybe we'll do some exercise on GPU at the end of the tutorial. So now you can discuss about Grace-Scott equation. So raw kernel are covered by other language, C++, ROS, Fortran, in Grace-Scott's course. So in this course, we'll only examine kernel fuse, QP fuse, and use of the QP version and Numpy version function. However, keep in mind that it's possible to have control over glide, blocks, share memory size, and stream with QP, as well as stream synchronization and event. If you are interested, you can go to this link. Now we have all the knowledge needed to solve a Grace-Scott reaction using the different finite difference method. For the Grace-Scott bench, you use stencil 3.3 with -8 at center and 1 all around. The output of image is full HD in a float 22. We keep we keep one image every 22 iteration, and write the HDF file for 1000 image in float 22. So for the finite difference, see the Numpy course. For the processing, Laplacian processing, you can use convolution. You can use the method convol2D available in the QP SYCL signal module. So you define your stencil like this, and you have an image, and to compute the Laplacian, just call. So the convolution function is come from QP SYCL signal convol2D, and to compute Laplacian, you call on your image with the stencil, with the boundary condition, same size, and fill the border with 0. For the time update, so we recognize all the parameters for the Grace-Scott reaction. You create a fuse kernel. With a temporary variable, UVV, and you recognize the layer champs to compute the time incremental, where LU is a Laplacian process like this. Now you have the Grace-code kernel as a Laplacian. You put it in loops. So you have two convolution to do. Here is a step frame, and you store the image V in array for each step frame iteration. The last step is manage all image and write them to a HDF5 file. I think it's not totally right. So I'll go to the profiling. If you want to profile this your QP script with Insight profiler, you call this the Insight profile QP and the name of your script. The generate a report, and you can show it in with Insight UE. And you have a GUI to examine the result. So actually, I don't know if already installed on must. So I'll show you some profiling obtained the previous year for this program. So you have two lines in the Insight profiler. One line for GPU, CUDA, and one line for CPU. So you see the activity of the GPU. All this I cannot zoom. It's a step. It's a step frame here. So here you write in memory your image, and at the end of the chunk, here you see the transfer memory. In a CUDA line, you have also two lines, one line for computation kernel and one line for memory. So you can see kernel computation, Laplacian, transfer of the image to the CPU, and the CPU writes the image on the disk. Return to the GPU, compute, transfer memory to the CPU, and write it on the disk, and so on. Yes. It's a very special kind of memory. You have a virtual memory. Maybe someone can explain, but it's a direct access to the memory without complicated allocation. I don't have no much. So it's not efficient. You can see your GPU don't work here, and the kernel stop during the transfer. So you try to improve this. So the first improvement is to parallelize the disk I/O. So you put the write of the file in a thread Python. So when you receive the memory to write on the disk, he put it in the thread, and the program can be continued, and we call the next iteration on GPU. So is this version? So when you write a parallelized version disk write, so it's more efficient. You see between memory transfer and kernel activity, you don't have time dead. And here you see the thread who write on the disk. For the first version, you take 20 seconds, and with this version, you take 40 seconds.
Expand the code of the parallel version so we can see the differences with the previous one?
Sorry?
Can you just expand the code for the parallel version just above the graph? No, it's, yes, here. Thanks.
The solution is here. You simulate your shock on GPU, and you create a thread with the image. Oops. Here you have the transfer, and the transfer is put directly in the thread. And the thread calls write HDF5 method. And here you have this line write on the disk. It's HDF5 syntax. So we create different threads. And at the end, you must wait all the thread finish, and you close your file. So here the next improvement is to use the double buffer method to parallelize kernel computation and transfer. So the exercise I propose for this morning's or maybe this afternoon, is to use the double transfer method with a stream to improve this. And in fact, the difficulty is to write a disk buffer asynchronously during transfer. And it's possible by using a stream dedicated to the transfer and call the lodge host function method, which allow launching a CPU function at the end of the stream. In fact, I go to the documentation. So here you have the class stream with a synchronize method, and you have also this function. It's a callback. In fact, when your stream is finished, it calls a C function. So the processing can be continuous on the GPU part. So the stream say, okay, I finish the transfer. Now you can run this CPU function to process the output. Oui.
You have another question on the Discord. Will the thread approach fully hide the write latency or just partially overlap it? In questions for teachers, the other channel. Go down. Again.
Pardon,
Yes, no, above. Above. Voilà. Questions for teachers.
Okay. While a thread approach fully hides the what's that thing? In fact, it's difficult. It depends of the vitesse of the I/O write. It depends of the system. Voilà. So yes, the lodge as function. So it's a very useful method. With this method, you can continue processing, start in a GPU and finish in a CPU. So it's necessary to use it for parallelize and manage the buffer we receive from the GPU. So conclusion, we have seen the main principle of Occupy. Porting program already written in Numpy and CPy is quite easy. However, the library remain open to feature similar to CUDA features, such as row kernel, pinal memory stream, which allow more refined use of GPU computing capability. So it's if you have a project with Numpy and CPy already wrote, and you want to port it on GPU, Occupy is a good library to do that without rewrite a lot of things. Do you have a question? So now we can have the exercise on GPU.
You have a question now on the Discord. Thank you. What would you say is the biggest strengths or weaknesses between CuPy and PyTorch? Both use CUDA under the hood, right? What is the difference performance-wise?
So CuPy is very close to Numpy, CPy than PyTorch. The biggest strength is it's very close to Numpy, CuPy. So there are many projects with this library, and with CuPy you can quickly port on GPU. The weakness, if you want performance, like transfer, you need to use a stream, to create stream to transfer. Maybe PyTorch have some automatic processing to parallelize transfer like this. So if you want to create a new project for GPU, certainly start it with PyTorch. But if you are already a project with CPU, you can easily port it on a GPU with CuPy. And the difference of performance with CuPy and PyTorch, I don't know exactly. I don't know exactly.
Last year class, we compared for the grayscale reaction, and it was 18 seconds for CuPy on our benchmark and 22 seconds for PyTorch.
Yes, it's less one. But the comparison for the both of the libraries, it's a hard question. So now I propose you to return to the exercise and use your GPU, maybe on your laptop or on Must, I don't know. For this course, we define some containers for Must to launch jobs. Maybe you can also have an interactive session if with GPU. I don't know. So the first exercise is je sais plus. Is this one? It's compare the function square on GPU and CPU. How many of you have access to GPU? One. Only one. Okay. Do you have an account on Must? Must? Ouais. All? Okay. So So in the same GitLab package, in GPU, you have a directory cluster, and with a README, how to submit a GPU job with an app tuner on must. So on must, I create two app tuner for GPU with CUDA 11 and CUDA 12. No, CUDA 12 first. And to use it, you must write a script. So there are 3 levels. You have a scheduler submission script that depend of your scheduler. So here at most it's HD Condor, but a Slurm script is also available, but not tested. So in this Condor script, you have in the first line the executable. So you put the script, this script, and you ask resources. So here your resources memory, 8 GB is quite sufficient for the exercise, and the type of the GPU. So here by default is A100. So this script is already wrote. Is step 2. In this script, we launch the app tuner with the good option for the GPU used, --NV for NVIDIA, and with some binding and some binding. So we go to the script level 2 run app tuner, script level 2 run app tuner. So for the first script, in fact, you don't change anything. For this one, you have your directory package, so you must change this one. The directory of the app tuner, don't change. It's already it's the good directory for must. And here you have the kind of image. So it's for CUDA 12. And you have some initialization for CUDA directory. And you call app tuner run. So they run a script in app tuner. So the script is this one, script level 3 in app tuner. So we have a template up. So the first argument is the path of your package. So here you can define the Python path. Here is set for the Python, the Grayscale Python package. They initialize the path and the LD library path for the CUDA library. And at least you have your script. So in this script, maybe you must change the Python path and the name of your script. So summarize, the first script, you change anything. The second script, you change CUDA version or the image. Maybe it's not necessary. And the script level 3, you must change Python paths and the name of your script. And when it's done, you can submit your job on the with a Condor submit and the first script. And for Slump platforms, is batch. It's okay. So here is a path where the obtainer are stored. You have the read permission, in fact. So I can help you if you want.
If must, I don't see this cluster.
Hi everybody, it's time for the coffee break. Maybe we'll continue exercise with Occupy this afternoon. So you will see 11 at 11. Thank you.
Okay, we're back for the Python GPU class. And now we're going to learn how to use cunumeric with our Grayscode code. So just to remind you, I'm in this repo on the GitLab, and it's this part. So GPU, and then you go to, right now it's going to be tutorial, and we'll take the second tutorial. Okay, Python GPU cunumeric. So this is just a README, you cannot run it. But in the README, you'll have some information on how to run the scripts that we're going to write. Okay? So we are going to, if you didn't manage to run on the MUS cluster or on your satellite site or on your GPU, we're going to have another session in the end of the tutorial to try and run codes on the GPUs. So we'll see that together later. Okay, so cunumeric, it's a library, and it's a library that was created in 2023 as a drop-in Numpy replacement. So the principle is that you just change your import. Instead of writing import Numpy as NP, you write import cunumeric as NP, and your code should be able to run on the GPU instead of a CPU. To do that, it's based on the Legate project. So it's a project that is made by NVIDIA. So cunumeric only works for NVIDIA GPUs. So it's a project that is aimed at democratizing distributed and heterogeneous computing on CPU and GPUs. And so it makes all the parallelization implicit. So you don't have to worry about the parallelization of your code. You can just change the import and it's supposed to work. So it's based on the Legend programming system and the Realm runtime system, so maybe you know about them. To install cunumeric, so it's fairly recent cunumeric, you need a recent Python, recent conda, and CUDA, I think now it's, in this tutorial, we're going to use CUDA 12 and 13. So as I said, cunumeric, it started in 2023 and it's still in its beta version. So there are still some bugs and the performance is not as good as other Python GPU libraries for the moment, but we're still going to test it on our Grayscode code. We can use it in our code with just changing the import here. And the cunumeric API, it covers 70% of the Numpy API. So we won't have any problem between Numpy functions and cunumeric functions. The interesting point about cunumeric is that it's supposed to scale codes from single CPU computers to multi-node, multi-GPU clusters without having to rewrite the code. So how does it do it? It does implicit parallelization. So you will have a little bit of time at the beginning of the execution of your program in which legate is going to write a graph, a task graph, and it's going to split the data into subsets, send the subsets to the processors, and in your task graph, it's going to organize the tasks so that they can be handled asynchronously. So, for example, in this example that they give, cunumeric, you can, legate will actually hide the latency of data transfer. So the copies of data here, they will be hidden because they will be made at the same time as the operations on data. Okay, so this is basically the first thing that you have to do to use cunumeric in your code. Normally, cunumeric is already installed in our Apptainer, so you shouldn't have trouble using it, but if you have, we'll see it together later. And to execute your program, so you don't do Python myprogram.py, you call the legate driver, because this will enable you to add some options. So you can choose the number of CPUs you want to run it, the number of GPUs you want to run. And you can choose the how many GPU memories you ask, the frame buffer memory here, and how many DRAM you want to reserve. So it's sysmem here. There are other options, but these are the principles that we are going to use. By default, legate will query the available hardware on your machine, and it will reserve it for all CPU cores and all GPUs, and most of the available memories. So be very careful that you have to always put these options in your when you run your job, because if not, it will use the maximum possible. If you run on the MUS cluster or another cluster, you will also have to be careful about the fact that you ask here for 2 GPUs, for example, then you have to ask in your submission file, condor submit or slum submit, you will have to ask for 2 GPUs. You have to be careful about the consistency. Okay, so let's try together with the simple example that cunumeric provides. So it's in the script directory here, okay, cunumeric Jacobi. So the goal is to run it on a CPU, to run it on a GPU, and to run it on 2 GPUs, okay, to see if cunumeric actually works, if legate detects our GPU, so because sometimes it can be a bit hard. So if the obtainer is correctly configured, it should work. So this example, cunumeric Jacobi, it's just an example they provide where they apply a Jacobi stencil over a grid just to mimic the diffusion of heat in a medium. So let's check this file. So you have 2 arguments that you can pass to this, this program. The first is the size of the grid. So we're going to increase it as we increase the number of processors we compute on. So from CPU to GPU, and then from the GPU to 2 GPUs, we're going to increase the size of the grid. And also the iterations, because you're going to do computation for a certain number of iterations here. You can also play on this factor here. But we're mostly going to increase the size of the grid to test this program. So what does it do? You have a grid here, and you apply some kind of stencil over it. And this is supposed to mimic the diffusion of heat in a medium in a simplified way. So it's already written, you don't have to modify anything. Here just I want to point out that we changed the import, cunumeric as NP. So every NP function, do we have some here? No, yes, NP here, it's gonna use the cunumeric equivalent, okay? And here, instead of using time in the Python time module, we're going to use legate.timing. Okay, it's just the benchmarking tool of legate, and we have to use it because, as you may know, on GPUs, when you time a program, it can be you can have a wrong output because the execution on a GPU is asynchronous. So sometimes, if you use just Python time, it will give you the time that the computation is finished on the CPU, but maybe the GPU will still run in the background. So with this function, you're sure that you're really timing the whole computation. Okay, so try to run this. Let's go back to the tutorial so that you can see how to run it. So first, to run it with a CPU, you can try to run it with a CPU. So you just have to specify the number of CPUs, the DRAM you want. And for the size of the grid, you can start with a 10,000 grid. Okay, try to do that. So maybe I will do a short reminder on how to run that on the cluster. If you are on your own laptop, you can just run this inside the obtainer, or inside your Pixie environment if you manage to install it, but you can have some trouble between CUDA 13 and cunumeric in Pixie, so I suggest you use the obtainer. So if you're on a cluster, let's check together how to run this. Oh no. Okay. I have to reconnect, I think. Okay. I'm going to do it later. So on your Grayscale Python directory that you cloned, you can go in the cluster directory, and here you have the 3-level scripts that Jean-Marc described earlier. So if you want to try to run on the CPU, the first thing you have to modify is this. You don't have to request any GPU normally. So you can put 0 here, I guess. But if you leave 1, you just ask for a GPU and not use it. You can do that. It's not a good practice though. On the level 2 file, you have to change here the path. So in must, I guess you're going to go to formation, SSH, and your number of SSH, and then your Grayscale Python directory that you cloned. The obtainer is located here on must. It's a already created obtainer, so you don't have to pull it yourself. You have to ask for, I guess here you have to change the name of the obtainer. So maybe you have to put CUDA 13, but normally with CUDA 12, no, I think you have to put CUDA 13 here, because I don't think, yes. Well, if you try CUDA 12 and then you have an error, then try CUDA 13 here. Here we run the obtainer. Okay, nothing to change here. And then if we go check the script level 3, so this is still the right path. This is okay. This you just have to modify. Instead of Python Grayscale QPy solutions, you put your execution commands. So legate, CPUs 1, sysmem, I don't know, 16,000, and the name of the script. So the script is script cunumeric Jacobi. So here you also have to change solutions to script. Okay. Okay, I'll leave you a few minutes to do that. Don't hesitate to ask questions in the room for the people on the MUS cluster. If you don't manage to run it, it will be a bit annoying after for you to follow the rest. So this is really a time to make sure that you're correctly running cunumeric and correctly using the GPU on the MUS cluster. And for people in satellite sites, you can also ask questions in the Discord. Did someone in the room already manage to run this on a CPU, for example? Yes. Okay. And on the MUS cluster, some people or not? Okay. So I'll leave you a bit of time. Discord there. Okay. I'm gonna check the Discord questions. Okay. So I'm going to answer the questions for the cunumeric. Yes, so here you have a problem. So I suggest for Isabel that you use the CUDA 13, the CUDA 13 obtainer, because I had the same issue on must. Yes, it was looking for a CUDA 12 library that was not present anymore on must. If you're on must, use the CUDA 13 obtainer. If you're on another cluster, okay, so there is another Um, okay, this error, I'm sorry, I did not get it. The HDF5, maybe someone has a solution in the chat, but I didn't get this error myself, and I don't know what could cause it. Yes, you have a problem with H5 but the problem is that we're going to need the HDF5. So I don't know, I'm sorry. Okay, so question from Michael. What is legate? Is it a job manager of your cluster or should we have it in the container? So legate is not specific to the Must cluster. It's actually an NVIDIA project, but we are going to use the legate driver, which is something that NVIDIA provides and that is installed when we install cunumeric normally. So when you do your when you install the obtainer, you should have legate. If you use Pixie with CUDA 12, you should have legate also. Let me know if you don't. Okay. Are there some questions? Okay, I'm going to check in the room. Okay, some people have some problem to install legate. If you use the obtainer, Michael, you should have legate. Maybe it's a problem of path, but if you use the obtainer, it should work. But to use the obtainer, you have to properly submit everything on your cluster with this. Yes, you have to put here legate, etc. If you have an error, maybe copy paste it, and I'll check later. But normally in the obtainer, it's installed. In the CUDA 13, it's installed, and in the CUDA 12, it's installed also. What does cunumerics differ than rapids? I don't know rapids actually. I've never used it. Maybe someone has an answer, or then if not, I can check myself. Okay, so I'll check later and I'll answer you later, Haifa. Okay, so let's try to do this together, but what's going on? Bon, tant pis. Sorry. Okay, so I'm in the Mus cluster. I'm gonna go to my directory where I cloned the GitLab. Okay, so here is the GPU. Maybe I can. All right. So I go on the cluster directory. I should be able to change this script level 3 in Obtainer. So I want to run the script that is inside the scripts directory. This I'm not going to use. Yeah, okay. Okay, so what I have to do is write legate. I'm going to ask for 1 CPU. It's better, yeah, no. If you run on your own computer, remember to write GPU 0 here, because if not, if you just run with legate and you put 1 CPU, it will use your GPU by default, because it takes the maximum amount of cores that you have. I'm gonna ask for this, and the name is cunumeric. What's the name? Jacobi. Okay. Okay, so I changed this and this. Now I'm going to. Sorry. The size, yes, thank you. Yes, I think by default you have one size, but it's gonna be super small. Yes, okay, let's put 10,000. All right, then I'm gonna check level 2 script. So here I'm on the MUS cluster, so I think I have to use the CUDA 13. Yeah. Let's just check that it exists. CUDA 13 latest. Okay, so I'm gonna use this container because I'm on must, and on must it's CUDA 13. Okay, so in this script I don't have anything else to change. In the level 2 script I have CUDA 13 here. This is the directory of the environment. No, this I should change. This is not the directory I cloned my direct repository on. Okay, so this is my my directory, but if you are on the MUS cluster, you should have SSH and the number. And then this is the directory that I cloned. Okay, so now it should be good. Let's try that. No, oops, forgot something else. Here I don't want to use CUDA 12, I want to use CUDA 13. Okay, and then let's check script level 1 because I have to, oops, to modify this one to, I don't want to request any GPU. I want to request one CPU. Okay, so this is just the beginning. I'm going to try my code on one CPU. I don't need a mail. Okay. And now I submit my code. So I think, yes. Okay, I submit my code with this command, _submit. All right, I can check my jobs with this. Okay. Are there any questions? Did you manage to do this step? Yes? Okay, I'm gonna check the questions on Discord. All right. So someone is unable to find the legate on must. You have to really specify the CUDA 13 on the scripts to run the obtainer, okay? Don't use an interactive GPU. Use the procedure that we told you. So it's what Jean-Marc showed you in the cluster directory. You really have to modify each script like I just did. So if you're on must, you should have CUDA 13. If you're on your computer, if you have CUDA 12, you can, I think you can still use the obtainer, or you can use the Pixie environment, I think. But if you're on must, you should use CUDA 13. Okay. It's another site. Okay. Okay, so please follow the procedure. If you are on must, you use this script, _submit. Then this script, where you have to specify CUDA 13 here. Be careful. And the directory where you have cloned your package, and then you have also to change this. Here GPU scripts, and here legate, and etc. Okay. Maybe my job is completed. Yes. So I just type ls. I see that I have some results here. So let's check the out. Normally, if everything, okay, so I guess I have an error. Yes. Okay, so I tried to run a CPU version, but the problem is the whole scripts are written for GPUs. So I just have to modify my submission script here. I'm going to ask for a GPU and not use it. Sorry, but it's going to be simpler. Okay, so if I ask to use a GPU so that I have all the CUDA libraries available, then I have to modify my level 3 script to be able to, yeah, I have to specify that I don't want to use the GPU that I'm asking for. You don't have to do this step if you don't want to do it. You can just run the benchmark on the GPU directly, but it's just to see that you can run the code on both CPU and GPU. Okay, so normally it should work. All right, I'm gonna go maybe in the room to see if there are some questions or if people managed. Is it working? Let's check the job. So it's over. Okay, so my simulation, it has taken 188 seconds. So now the goal is to redo the same thing, but with one GPU and a bigger grid size. So tutorial, yes, here. So I managed to run on a CPU. Now I want to run on a GPU. So I'm going to copy paste that. So here you just have to be careful about specifying GPUs 1, specifying the frame buffer memory, and the size of the grid. You have to augment the size of the grid. Okay, so if not, it will not be very useful to use your GPU. Okay, so let's do this together. Script level 1, I'm going to ask for 1 GPU. Okay, I have it. Script level 2. I'm going to check, but nothing to change here. And I just have to change script level 3. Okay. And here, okay. So, all right. I'm sending it to the scheduler. Okay, so I sent a job asking for 1 GPU, and with the legate driver, I asked to run my Python code on a GPU. And yeah, remember to increase the size of the grid. If not, you're not going to use the GPU properly. Okay, maybe we can check. Yes, do I have an error? Okay, so now, well, it's much faster, so it's 2 seconds instead of 100 or 200. Okay, so this is what we expect from going to CPU to GPU. And then the last part of this little exercise is to ask for 2 GPUs and run them. So notice that we didn't change anything in the code and we managed to run on CPU and on GPU. Now let's see if we can run on 2 GPUs. For this, we also have to increase the grid, because if we don't, then we're not going to use our GPUs at 100%. So for this last step, what you have to do is change the submission script, Condor, ask for 2 GPUs. Okay, it should be good. And of course, change the execution command here. So yeah, I think I copy pasted it. All right, so here I asked for 2 GPUs. I increased the frame buffer memory, so the GPU memory, and I increased the size of the grid to have to make use. Oh no, je suis déconnectée. Sorry. To use the 2 GPUs to the fullest. All right, I have to reconnect. Sorry. Thank you. So normally my, no, I haven't submitted anything yet. I'm just going to check that my script, yeah, okay. Okay. All right. Okay, I'm going to submit the last part of this little exercise here to check that I'm able to run on 2 GPUs also. Maybe you're going to stay a little bit in the queue because you're asking for a lot, actually. but it's okay. Oh, it's already running. Okay. So it should also take a few seconds. I'm gonna check the questions on the Discord maybe by the time. Okay. So you should have legate inside of your container because it's installed when we install cunumeric, and in the obtainers we install cunumeric. So it's available in CUDA 12 if you use the CUDA 12 obtainer. If you're on must, you should use the CUDA 13 obtainer. All right, let's check my last job. Okay, so now it ran on, it took 9 seconds to run. Why is that? Is because, so it's almost the same time as the 1 GPU version. Here we were running on 2 GPUs. So why is it the same time? Is because we increased the size of the grid. Okay, we have a much bigger grid. So if we were to keep the same size of the grid, I'm not sure it will be faster because then the GPUs would not be used to 100%. In this example, what is interesting is when we increase the data, the size of the data, we are still able to process it at the same amount of time. So this is an example of weak scaling. Okay, it's one of the things that cunumeric is showing in their documentation and as their goal is to be able to process the more data in the same amount of time when we increase the number of cores we compute on. So when we go from CPU to GPU or from 1 GPU to 2 GPUs. Okay, did you manage to run this little example here? Yes? Are there still some problems in the room? No, it's okay? All right. So for the last part of this cunumeric tutorial, we're going to try to run our Grayscott code with cunumeric. So what do we have to do? The goal is just to use the same code and change the import statement. This is what cunumeric advertises. It's just a drop-in Numpy replacement. So we have the script in here, all right? There is the equivalent solution, but try to open the script and change some things yourself. So we don't have any code server or stuff like that. Just try to edit it using Nano or Vim or anything. The first thing you're going to do is change the import here, import cunumeric. And then, yeah, I forgot to change this. So this should give you, when you time, where is it? Okay. Yes, here, this is using the time module. Just change it to use the legate.timing module. So you just have to remove this first time here. Okay, you just call time. Yeah, because we have to properly benchmark with the legate.timing module. Okay, try to do this yourself, and then I think, yes, we're going to change a few things afterwards. So basically what I have to change here is import cunumeric as NP. And this time module that I was trying to use the Python module, but I'm going to use the legate.timing module, and I imported it this way. I think it should work now. Okay, if I want to run this, I have to go back on my script level 3 in the cluster. Okay. In the cluster, so I'm gonna ask for 1 GPU. Yeah, maybe I can keep it like that. So the name of the script is Grayscott cunumeric. Let's remove that, and then I'm gonna give some arguments because let's try with a small set. With a small number of images for the moment, so I'm going to put 100 images. And the chunk size, I think by default it's 80 images, so I don't know, maybe we're going to do 50 images. And this steps is 32 by default. This we're going to keep it this way. Okay, so with this command, I'm running my my Grayscott cunumeric script. I have to change the level 1 script as well to ask for only 1 GPU. All right. And I can submit it. Oh. Okay. Is it okay in the room? It runs? Yeah. Okay, first I'm going to check if my job worked. Okay, so 36 seconds for 100 images. It's not great. So I'm going to show again the modifications I made. First in the level 3. Well, I have to rewrite them anyway, so perfect. So I asked for 1 GPU. The GPU memory, I think, what did I put? Well, for 1 GPU, maybe, yeah, maybe I'm going to put 15,000. Okay. So these are the legate options. Then I have to call my Grayscott cunumeric script. And then the options of the Python file, it's true that I didn't explain them, so I'm going to explain them now. You remember for the CPU class, we had all this Jupyter notebook that we were running. In this case, we put the whole script in a Python script here. Whoops, this one. So to run this script, since we are not on a Jupyter anymore, normally you should do Python and the script.py, and then we also added some arguments so that you can configure the script when you call it. So you can specify the width and the height of the images, but this is by default we use HD. You can specify the number of images. Sorry. Is it okay? The number of images, this is what we're going to use to shorten a bit the execution time, because the real benchmark is on 1,000 images, but with cunumeric it's going to be a bit slow. So I suggest we put 100 for the moment. The goal is to modify the code so that we can compute 1,000 images. These steps we can leave it to 32. And then you have all the arguments here that you can change, but it's going to change the Grayscott reaction, so you're not going to have the same results. And the chunk size here, remember in the CPU class, we added it because we did not want to compute, like to save 1,000 images at the same time in our array and in our HDF5 file. So we compute, like, if we define chunk size equals 50, we compute 50 images, we save it in the HDF5 file, and then we resume the computation for the other 50 images. So this is going to be useful to handle the memory of the GPU. So since we are not making any changes in our script, in our Python script, we're not making any changes. The goal is just to use cunumeric instead of Numpy. We have to take care of the fact that on the GPU, the memory is limited. So yeah, maybe if you don't change the chunk size and leave it to like 100 or 500, maybe it will start to use a little bit too much memory on the GPU. Okay, so to modify the by default values, you just write the option here and then the number. So I'm gonna do maybe like that. I'm gonna test and see if it works. Yeah, so this is what I did, and it was 36 seconds. After the lunch break, we're going to modify the Laplacian in our cunumeric script. Yeah, so this we made the first change that we wanted to do, and after the lunch break, we're going to do the 2 and 3 and 4. Yes? The command? Pourquoi ça marche pas? Okay. So you have to specify the legate options. Okay. 1 GPU, memory 5,000. The name of the script. So it's in the script directory. If you made the changes yourself in the script directory or in the solutions directory, it's the equivalent but already corrected. The number of images. And the chunk size. Here it's not a dash, it's like a underscore. Okay. If you want, before the lunch break, I can go check in the room if there are some questions. Are there some questions in the Discord? No, I guess it's only for installation. Okay. Are there some questions on this class? Yes? How do you choose it? So normally you should adjust it with the size of the memory that you ask for. With cunumeric, I'm not sure how it works because I've had some issues because even if I try to, so with this chunk size, it will ensure you that you will only allocate at the same time a specified number of memory, okay? With cunumeric, I'm not sure that it works this way because the problem is sometimes the memory handling in cunumeric is a bit obscure, and there have been some occurrences in which I had to reduce the chunk size because I think it was allocating too much memory as opposed to what I asked. So try 50. Usually it works for me on the mass cluster, but
Is there any rule of thumb to decide?
this is just how I made my code. So the thing is, it's 50 images, 50 HD images. So you have the size of an HD image, you multiply it by 50. You have the number of RAM that you would require. On the CPU, it works. I mean, it works well to define it. On cunumeric, sometimes I have surprises. Other questions? Okay, thank you very much. And then we'll resume afterwards to finish this cunumeric tutorial. And then we'll do the JAX tutorial. And Jean-Marc will also present binding C++ in Python.
Okay, thank you, Alice and Jean-Marc, for the presentation of this morning. So we'll have a lunch break now, and we will resume at 1:30 as always. So we'll have the presentation of the Croatia data center, and then we'll start with some wizardry with Python, as you said. So have a great lunch.
Okay. So welcome everyone. We're here with Croatia and with Emir Imamagic, who will introduce at the University of Zagreb and the Competence Center, SRCE, who is partnering with us for the Grace Code School. So Emir, we can hear you and the floor is yours.
Thank you for the introduction. So as you can see at the upper part of my slides, SRC basically means heart in Croatian language. And we are celebrating a 55 anniversary since we have been established this year. So we have been around for quite a while. I'll try to explain what all kinds of activities that SRC is doing in Croatia. We are part of the University of Zagreb, but we are basically providing a lot of services on the national level. So right now there's around 180 of us. So we're not that big. We are located in 3 locations. On the left side, you can see our main building. So the main building was quite famous because that was the one that we built 55 years ago, and it was actually built in order to house a big supercomputer. Well, so supercomputer in those standards back in 71. And it's still our main building. On the right side, you can see a building which was built as part of a big project which we finished 3 years ago. And basically right now we're sitting in this building. So we have about 30 different services, and our main customers are academia and scientists and researchers, though we do have some services covering the other areas like SMEs, industry, and public administration. But basically, our main customers are academia and scientific community. So moving on, so we have this really nice cycle. So in the sense of a research, we try to cover all the needs. I'll go through individual services in a moment, but basically, so the AI, so authentication and authorization infrastructure. So we do provide the federation for the Croatian academic researchers. There's the Croatian Research Information System, which basically holds all kinds of information about the active projects going on, about the publications being done, about the instruments, about the services, about the other thingies. So basically, we do host the official Croatian Research Information System. Then there's the education and specialized support. We have all kinds of different education related to the service that we provide, but also to a more generic things like, I don't know, system administration, how to handle documents, how to store data in repositories and so forth. So the 2 biggest services which are relevant for the research in open science is the computing part, so where we enable people to do analyze and processing, and on the other hand, the data where we enable people to share, preserve, reuse, plan, and collect. So there's several different services there. I'm pressing the wrong one. So trusted identity, as I said, so we do provide around 1 million electronic identities. So it's basically, yes, all of you have your own institutional identities, which you basically use to access different services. So this is what the SETSA is providing. There's almost 1,000 services which are utilizing the AI infrastructure. There's over 200 institutions, and then again, once you go outside of Croatia, you can use the other room. I guess for all of you students in the crowd, you know what the other room is. So basically, if you go in over 100 countries, you can access you can access the Wi-Fi for free or some other services by basically using your institutional identity. With regard to the information system, there's a really, in our 55 years of existence, we developed all kinds of different information systems, sorry. So the CNRS, as I said, is the one with basically this is the Croatian national information system for the science, and it contains over 16,000 projects, 50,000 users, 130 institutions, and as I said, we collect projects, users, scientists, and there's almost 1 million publications which are being reported there. Other than CNRS, we also maintain the information system for the higher education. So basically, all the information about the what kind of classes you go to, all the grades that you get. So basically, if you want to improve your grades, you can start working for CC and then improve your grades there. Moving on, so data infrastructure services. So we have 3 of them. We basically built a framework where all the repositories are stored. So basically, all the academic institutions are storing their data in the repositories on top of Dava. So right now we have almost 200 repositories. Basically, it's a multi-tenant system, so you get your own like an admin access, and then you store there whatever kind of things you want to store. Right now we have over 333,000 digital objects stored there. There's a publications, data set, so it's basically you can store their presentations, you can store your final works, so your diploma thesis, your doctoral thesis, so basically any kind of digital object can be stored there, and there's over 180 of them. We also have the scientific professional journal storage with over 300,000 articles. It's a slightly different thingy from Dava, but it's been well used nowadays. So we have over 500 journals storing their articles in there. And finally, we have a system called PUH, which is basically used for sharing data during the research. So it's an Nextcloud platform thingy where you can basically, right now we have over 100 terabytes of data stored there, over 800 users and over 300 research projects which are using this platform for sharing this data. Actually, it's interesting, the PUH is connected directly to the advanced computing platform where people can calculate things, basically do the number crunching, but you can also access PUH and store the data or grab the data and pull it and store it on the advanced computing platform. So with regard to the computing infrastructure resources, which is basically the area that we are working on, and basically for a few from Croatia, we're using the resources that Martin sent you information about. You're on one of these guys. So a couple of years back, we had, well, actually, it was 15 years ago when we started the project, but it was put into production in 2023. We built three big resources, Supercomputers and Stampar, which are providing a computing infrastructure for academia and researchers in Croatia. Basically, it's a tier 1. We are part of the EuroHPC, but we do not have a EuroHPC resource in Croatia. So basically, we do not have a tier none, but we do have a tier 1. So one resource is supercomputer. As you can see, usually when you look at a picture of a supercomputer, you will see a bunch of boxes. In our case, it's just one box, but it gives us a 1 petaflops performance, 1.25 actually, and it's actually quite interesting. It's a directly liquid-cooled system, as you can see on the picture. So these blue and red thingies are basically pipelines where where you have the direct liquid which is cooling the machines, which makes it quite efficient in a sense that we do not spend too much money on cooling. So as I said, 1.25 petaflops, we have around 10,000 processor cores, well, 8,000 something. We have 80 GPUs, so these are NVIDIA A100s. The older ones with only 40 gigabytes of memory on it. There we don't have the 80 gigabytes. But you know how it goes, the supercomputing works. It has been in production for 2 years now. Things break, and because on the market there are no A100 with 40 gigabytes, so actually we now have 2 nodes with these custom A100s with 96 gigabytes. So we actually have 1 queue with 8 of the 96 gigabytes GPUs. All over, there's like 32 terabytes of normal RAM. This is not the memory on the GPUs. We also have around half a petabyte of all-flash storage. So this is a cluster store, so basically cluster underneath, and it's working quite smoothly. People are really happy with it. From time to time, we have a problem where users really quickly fill all the space if they have some problems, but we are working on that. Right now, the whole service has over 1,000 users, and we have over 250 projects. Together with the supercomputer, we also built a cloud thingy. So this is basically infrastructure as a service, which is based on the OpenStack and Ceph. And actually, the platform that you're working on, for all of you from Croatia, which are using our resources, it's basically on OpenStack and Ceph. There we have around 11,000 CPU cores, and unfortunately only 16 GPUs, and these are well used. So basically we have like a waiting list. If somebody wants to have direct access to the GPU, they basically need to wait in a line for other users to finish the usage. We also have some large memory capacity there with 2 terabytes of RAM per node. So basically these are our advanced computing thingies. So CERSI is also participating in a lot of different EU projects. This collaboration with the Grey Scott School is being done through the EuroCC project. We still have a logo from EuroCC2 because the EuroCC3 grant agreement hasn't been signed yet. So whilst they're waiting for the visuals and for the project to officially start. But it's kind of, what is it now, June? Yeah, so we have been working now since beginning of April without the grant agreement being signed. But anyhow, we're working and trying to push the HPC around and promote and so forth. We're also participating in ProQCI, which is basically a project which is building a quantum computing, communication infrastructure in Croatia. We're part of the EDIC, which does the similar thing as the EuroCC, and then there's a bunch of different EOS-related activities, which are basically focusing on building the European Open Science Cloud, which is something really abstract, but we are working hard on making it less abstract and more something which is actually put into use. Finally, with regard to the infrastructure, as I said, today's participation and all our participation in this school is part of the National Competence Center for HPC, where we collaborate with 36, I think the latest number is 36 competence centers in Europe and around. As I already mentioned, we are maintaining the authentication and authorization infrastructure for Croatia, all kinds of different information systems, and we are the mandate institution for the Open Science Cloud in Croatia. We're participating in different edicts. With regard to the data repositories, we are the national RDA node, and we are the e-learning center for Croatia. And that would be that Chrome piece. That's a site. If you have any questions, this is an official address, but both Martin and me are on the Discord channel, so you can ping us directly if you have any questions with regard to the school or with regard to the subset in general. Thank you for your attention.
Well, thank you. Thank you very much, Amy. I don't know if you heard the claps here, but we have also around 300 people connected who watch your presentation. So if you have any question, as he said, you have the email, you have the dedicated channel on the Discord. Don't hesitate. And we are very happy to have you with us. And let's continue the Grayscale School. Let's meet at 2 and see you soon, Amir. Bye.
Thank you. Bye.
And we are back on the Grayscale School, so we'll continue to do some wizardry with Python on GPU with Alice and Jean-Marc. So Alice, it's up to you.
Thank you, Pierre. So I suggest we spend the next 30 minutes to finish our cunumeric example, and then we'll move on to JAX. Okay, so if you had trouble installing cunumeric, I'm sorry, I had a lot of trouble also. So if you didn't manage in the end, it's not that bad. We'll just spend the next 30 minutes on it, and then we can move to something else. JAX will be much easier to install and to use. So we were at this point, so we finished running our example, and now we're in the tutorial part where we want to run Grayscale on our GPU, okay? So these are the changes that you have to make to your Grayscale cunumeric script. So as I said, the Grayscale cunumeric script is in scripts here in the GPU directory. And so it's this file here. You have to adapt it, so change the import statement to use cunumeric instead of Numpy. Change the timing function also to use the legate.timing instead of time. And then I suggest you replace the Laplacian with a dedicated cunumeric function. So let's open this and I'll show you. In our previous class, the CPU class we met last week, we wrote this Laplacian that uses just NumPy broadcasting on the arrays. So the goal here is to replace this with a convolution function that is actually enabled in cunumeric. So be careful here, it's a bit of a workaround because if you try numpy.convolve, it might not work, I think, but cunumeric has a different implementation than numpy for the convolution function. So with this, this function, you can actually convolve 2D arrays. I'm not sure it's the case for numpy. So you can use cunumeric.convolve to compute your convolution instead of computing the Laplacian here by hand. So you convolute your stencil on the U array. And that's all. And then the next step is to modify the rest of the code to follow the best practices, because in cunumeric, the best practices are kind of the same ones with than the best practices with NumPy. So let's check so these are all the best practices for cunumeric. Be careful that, to be on the latest version here. We're going to check together, but most of the good practices, we already have them implemented in our NumPy code, which is normal. There are a little bit of differences between cunumeric and NumPy, I think, for indexing. I think fancy indexing is not working much in cunumeric, but I don't think we use some. And what we're going to maybe do is, I think most of this we don't need. Maybe this we could modify in our script. Instead of doing in the Grayscale reaction u equals u plus, etc., we can do a numpy.add. Okay, you can try to implement some replacements like that. There is a solution in the solution directory, but I'll leave you maybe 5 or 10 minutes to do it yourself, and then we'll check the solution together. So as I said, the steps that you have to do are these ones. Change the import statement. Okay, change also the timing function to use legate.timing. Change the Laplacian and replace it with convolve by cunumeric. And modify the code to follow the best practices. All right. If you have some questions, ask them in these 10 minutes. Yes? Can you repeat in the micro, please?
For the cunumeric convolved,
Yes.
since it's supposed to be different than the one from NumPy,
Should we keep the same, the mode same and the method direct or automatic?
So I don't remember which.
Because I remember last week you said that we used the mode same because we wanted it to have like the same
Yes.
dimension at the input arrays.
But it was the SciPy
Yeah.
convolve function. Okay, so I think it's not the same here because, for example, we had to also specify the boundary. We had to put boundary equals wrap, and here
Yeah.
it doesn't exist.
Yeah.
Yeah, I don't remember for exactly what are the options here. You can try and see if you have the same results when you vary these. I know on the solution that I made, the mode and the method, they work. But yeah, I would say maybe try and see for yourself.
Okay, I'm gonna try it. Yeah.
Okay, let's check on the Discord. Send us this page of the instructor. Do you mean this page, maybe? Yeah. And the documentation, you can click on the links. I think this link is broken, but this link works, and then you can search for Convolve inside. Okay, and then if you want to run your program to test it, you have to run it the same way as we did before with everything that you have in your cluster repository, if you are on a cluster. Yeah, so that was it actually. Okay, try to do it yourself and then I can answer some questions. the modifications we have to make. So the first modification that you had to make was just change the import, but maybe you did that before the lunch break. Here the timing function is legate.timing, .time. And then the Laplacian here, I used mode equals same to do the convolution. Okay, I guess if you try some other modes, it might fail with the, because maybe our arrays are not the right size. I'm not sure. Okay, for the init arrays, nothing to change, I think. But if you see some things that are that would be better in another way, you can still rewrite it according to the best practices. But here it was okay. This we could change. Instead of the u equals u plus, we do an np.add, and same for v. Well, it doesn't make a big difference, I think, but you can still do it. Simulate images, I guess we didn't change anything. This one either. Okay, and so here the function for time is just time because you imported it with the legate.timing. All right, so let's submit this. Yeah, so this is the whole file. Let's submit it. So for this, I'm going to submit the solution script directly because I don't want to rewrite everything. Okay. So here I have to specify solutions instead of scripts, but if you modify the script in scripts and you want to test it, you should stay with this. Okay, the sysmem, I can keep it, why not? The name of the script is cunumeric solutions. The arguments, remember, for our script were n images. Here, I guess we can try with 1,000 to make our final benchmark. Let's do this. And the chunk size, I think I'm gonna keep 50, but maybe a bigger size would be good, but it depends on the memory of your GPU. And in my case, I think I'm asking for an 800, so there should be no problem, but I've seen a little bit of problem when I increase this chunk size, so let's try like that. It might be a bit long, but okay. And then I'm gonna script the other, change the other two files maybe, no. This is okay. Level 1. I'm asking for a GPU, I'm asking for an 800 GPU, and that is good. Okay, let's submit this. So I'm submitting my job. Okay, and it might take a few minutes to execute because I asked for 1,000 images. So this is the final benchmark. And if it works, I should find my results in the results directory here. Well, so I already have a few because I made some tests before, but it should update. And then I will have this project.avi, I think, which is the final video that is made. So if you want to retrieve it, you can copy it on your laptop with SCP. We're going to see afterwards how to do that. Okay, so let's wait for the... Oops, I think I have an error because it's not supposed to be this fast. Yep. Ah, yeah, okay. I'm gonna check the name because maybe there is something wrong. GPU solution. Okay. Well, I'm gonna try again, but I don't know what I did wrong actually. Submit. Okay, so did any of you manage to run this Grayscale cunumeric.py on the cluster or on the laptop? Yes? Okay. Is it fast or is it slow? It's fast? How many seconds did you have in your... Did you do 1,000 images? You did on your laptop? Did you do 1,000 images? Okay, yes.
Took like 1 hour to do all the thing with the video. Now I just when I changed to Converge, I just put like 32 images. But when I see the factor of amplification, I think it's gonna take like 40 minutes with 1,000 images. But I have a small GPU. That's
Okay.
really why.
But that is slow though on the GPU. I mean, it's faster than before, but compared to CuPy, did you try the CuPy one?
I didn't.
Okay. I know on the MES cluster we have like 20 seconds for CuPy and JAX and 200 seconds for CuPy numeric, so it's like 10 times slower. But maybe I'm not using it the best way possible. In any case, in this Grayscale code, it's not really performant. Okay. Okay, so I'm going to wait a little bit for my benchmark to finish. I'm going to show you how to retrieve the video on your laptop. Okay. Okay, so when I want to connect to the cluster, this is the command I have to type, okay? If you go on a different cluster than us, it's going to be a different address here, and then, of course, you're not going to have the same name as me. So if I want to copy my results to my laptop to be able to actually play the video, because on the MES cluster or any other cluster, I don't think you can play the video. So let's copy it to my laptop using SCP, which will use SSH to copy from the cluster to my laptop. So I just do, on the cluster, I take the full path. Oops. I have to specify the path, but okay. So it's on GPU results, and I think the name of the video is going to be project.avi. Yes. Yeah, okay. I'm going to take this this video. It's going to be the one I made with 100 images, but it's the same. Project.avi, and I copy it here, let's say. Okay, so now I can try opening it. Where is it? Project.avi. Okay, so this was made this morning with 100 images instead of 1,000. So it's the beginning of the simulation. Okay, and then if you do 1,000 images, it will grow bigger and bigger, and then you'll be able to witness it more, well, better. Okay, so yeah, this is how you can copy it to your machine and to open it. I'm gonna check my benchmark to see if with 1,000 images it's done. No, it's not. Okay. Are there any questions on this cunumeric part? No? Okay. So I guess we can conclude on this. I'm going to put the results of the benchmark that we had last year, I guess. Yes. So last year, these were the results of the benchmark with the 1,000 images that we had. This year, I don't know why, but it's even slower. Cunumeric, I only managed to have like, yeah, maybe 200 or 300 seconds. So it's not great. I don't know why. I tried to profile the code. If you have any idea, let me know. But yeah, so it was just a test of cunumeric to see if it could work on our code. It's not great. In the Jacobi example we took, it was much better. So I guess it depends on the codes. It's not easy to know what's wrong, because the goal is just you change from CPU to GPU very easily, but then you don't really have to modify anything to fit the GPU, though, so it can be a bit, it can hide a lot of the problems. So yeah, I guess if you want to use cunumeric, my advice would be just try if it works with your code, and then if it doesn't, don't spend too much time on it, because it's still a bit, it's a young library. It's still in beta development, so maybe in the next year it's going to be a bit more performant. 2 years ago, the performance were much worse, I think. I'm not even sure I managed to make it work with the Grace code actually. So yeah, maybe from year to year it will improve. All right. Yeah, it's still running. Okay. So it's been running for 6 minutes already. Oops. Okay, so I suggest we move on to the JAX part. Is it okay? Are there some questions? No, okay. Let me check the Discord. No questions, I guess. Okay. So for the JAX tutorial, we're going to take maybe 2 hours to do it. It's going to be a bit longer, because in the CPU class, we could not start the JAX implementation. We didn't have time. So today we're going to do the CPU implementation, and then we're going to run it on the GPU also. So JAX is going to be the same principle as cunumeric. We're going to run indifferently on a CPU or a GPU, almost indifferently. So let's take the number 1 tutorial here, Python GPU JAX. And then we have all the other things that we are going to use for the next 2 hours. Okay? So Jean-Marc presented JAX last week. We're going to try to use it on some examples and then on the Grace code. So JAX is really easy to install. You just have to be careful that when you install it to run on the GPU, you install the GPU version. So yeah, there is a, I think, detailed explanation here. So you have to ask a JAX bracket GPU, something like that. It's also made for NVIDIA, but also AMD GPUs. So this is a good point. The only modifications you have to make from a CPU, a code that you will run on CPU, is you can add some XLA optimization flags when you run on a GPU. So they give a number of examples here on the documentation. Here are 2 examples. This one is for matrix multiplications, I think. And this one, yeah, is to hide some latencies, I guess. I think we're going to use just the first one in our Grace code, because we don't do any matrix multiplication. Yeah, but apart from that, you should be able to run the same JAX code on a CPU or on a GPU. However, it's not as cunumeric. We don't change Numpy with JAX. It's not the way it works. We have to rewrite our code to fit JAX. So as Jean-Marc explained last week, JAX uses JAX arrays. So you have to declare your arrays to be JAX arrays. We're going to try to see 3 constructs that are very specific to JAX but are really efficient, and then we're going to use them also in the Grayscott code. The first concept is VMAP. So VMAP in JAX is a tool for automatic vectorization, and it would map a function over the argument axis. So, for example, if you have a function that computes the derivative of a vector, and you want to apply it to an array of vectors, you can use VMAP to apply the function to the batch of vectors without having to say, okay, apply this function on this index of the array of vectors. So it's quite practical, and also it uses the performance of vectorization. So the first thing that we're going to do is take some examples here that are very simple. So what you can do is open the JAX VMAP script. It's in a GPU script, and you click on it, up. Normally it should work. Okay, so this is a script that you have to transform to use JAX instead of what we have here. And so what you need to do is to use the VMAP tool to map the computation over the vectors in the vector array. So here, let's take a look at this. We have a function that computes the norm of a vector, okay? It takes the 2 coordinates and computes the norm. We have an array of 100,000 vectors, okay? What we want to do is compute the norm of these 100,000 vectors. So here, in this example, we use just Numpy. We're going to use the for loop, okay, to say, okay, I want to compute the norm of all the vectors in the vectors array. What you can do with JAX is actually remove this for loop and use VMAP instead. So try to do it yourself, and then we'll see the solution. The solution is in here, so JAX VMAP solutions in the solutions directory. So yeah, basically you have to replace this for loop and use VMAP. So please check the documentation if you can, because this will tell you how to do. You're going to see it's a bit hard to understand the arguments that you have to pass, etc. It's going to take a bit of a while to get used to JAX, but then once we really master the JAX syntax, it's going to be much easier, and then it's going to be quite fast. Okay, so I leave you a few minutes to do this. If it's too easy, you can move on to the other examples also. Yeah, and then I guess in maybe half an hour we'll switch to the Grayscott code. Okay, I leave here the VMAP documentation. Maybe. Okay, here are some examples of the VMAP use. So if you already wrote the VMAP here, you can try to run it. So, okay, first is, okay. I'm just going to check the CUPy numeric output, just real quick. Oops. Oh, okay. Sorry. Okay, so if you want to run your JAX code, you have to modify the level 3 script. Well, so here I'm going to run the solution, but if you modify the script, you have to here put script. So we don't use legate anymore because we are on the JAX. And I'm going to run, so it's not grayscale JAX solution, it's JAX vmap.py. So normally this should work on the cluster. Yes. Okay. I don't think I have to change anything else. So let's just try that. Okay. I'm going to check this one quick. Okay, so my CUPy numeric benchmark actually, I don't know why, but it took 800 seconds. No, I don't know. It shouldn't be that long. Okay. Ah oui, okay. Never mind. Okay, so let's check the solution together. So you had to replace the for loop over the array of vectors with a vmap that will map the norm function over all the arrays that we have. Okay, so here, if you take the documentation, they tell you that you have to use vmap on a function and map it on the array. So here we have our function norm that we didn't change. We are just being careful that we use jax.numpy as jnp. And here instead of numpy.sqrt, we write jnp.sqrt. Okay, we're going to see that after also, if you didn't know. So here, I think Jean-Marc explained it last week, but we're going to see it afterwards also. We can JIT our function, JIT compile our function. And to use the vmap here, we use it on the norm function, and then so we declare a new function that is called batch norm. That will be the function that computes the norm on all of our batch of vectors. All right, and so we call this function batch norm on the vectors array. Okay? So it's a bit weird if you never used it, but this is how JAX is going to be really efficient. Did some people have trouble writing this? Yes, there is a question here. I think you have a microphone here. Yeah.
Yes. Does this work? The shape that I get is either 2 or 100,000, but how do I get 100,002 as a result shape?
Ah, as the result dot shape here?
Yes, because I only see in what is it called?
Are you sure
in axis as a parameter?
You're using this JAX vmap solutions?
Okay, I will try again, I guess.
Yeah. All right. Can I move on to the next exercise, or are there some questions on this vmap construct? Yes, question here. Can you pass the microphone to the person here? Thank you.
Is a just-in-time compilation necessary?
Sorry?
Is a just-in-time compilation necessary or optional?
Good question. I think it's necessary, but yeah, let's check. Maybe not. Did you try without it?
I did. It took me a lot of time to run, but in the end, it is managed to run. But I don't know if this is good.
Yeah, so I guess it's not mandatory, but then yeah, since you're going to apply this function on a lot of elements, I think it's better to JIT it. Yes. All right. Are there some questions on the Discord? Nope. Ah. Okay. Is there a rule of thumb regarding when to place jax.jit decorator? So we're going to see it on the Grayscott implementation, because there are some functions where we cannot place it. I guess it's better to test if you can use it, and if not, you just remove it. A lot of times it won't work because, as Jean-Marc showed it last week, you have specific requirements to fill when you want to JIT compile a JAX function. A rule of thumb, I would say, yeah, when you have like a computation made in a function without external libraries, instead of except NumPy, and that you want to apply this function to a lot of elements, I would say it's good to JIT compile it. All right, so let's move on to the next exercise. So I'm gonna go back to my tutorial. The next exercise is the JAX for E loop. So in the VMAP, we replaced our for loop with a VMAP on the elements of an array. Now we're going to replace a for loop with for E loop. That is more similar to a for loop, but it's just faster because it's in JAX. How does it work, the for E loop? You can open the documentation here. So it will run a fixed number of iterations sequentially, like the for loop, and it will return the last value. Why do we use it? It's not necessarily faster than the Python for loop, but just if you want to use a Python for loop with JAX, it might be very long because in JAX, when you compile a for loop with Python, when you compile a Python for loop with JAX, the compilation time will scale with the number of loop iterations. So if you do 1,000 iterations, it will take forever to compile your for loop. So this is because JAX unrolls the loop to compile it. So the thing is, we have to replace Python for loops with either other JAX construct like VMAP, etc. when we can, or if we don't have any equivalent, we just keep the for loop, but instead of being a Python for loop, we use a JAX for E loop. Okay, this is to avoid a compilation problem that is very specific to JAX. So the next step is to open the JAX for E loop script and to replace the for loop with a JAX for E loop. So this is going to be a bit tricky because it's not as easy as a Python for loop. You have to define a function that you will execute in the for E loop. And then, you have to be careful about the type of your function, the signature of your function. So read this part here. Try to adapt the JAX for E loop here accordingly, for I loop, sorry. Yes. So if you try to run this as is, I think it might take a while to compile if you do a lot of iterations. Because you have a for loop on the length of x, and here the length of x is, I don't know, 100 elements, 1,000 elements. So it might take a while to compile. So you have to replace this for loop here with a for I loop of JAX. And for this, you have to declare a function, specific function. And it's all explained in the documentation here, but it's a bit cryptic, and you don't have any example. Yeah, sorry. So try to do it yourself, and then we'll check the solution together. Here. Someone specified that it's not useful to JIT compile a for I loop. Yes. Because a for I loop is already compiled, JIT compiled. Okay. Are there some questions in the room or in the Discord? All right, so I'll leave you 5 minutes to check this for yourself, and then we see the correction. Did you manage to change the for loop in the JAX for I loop? Do you need more time? All right, so let's see the correction together. So the goal is to remove this for loop here, because it will take forever to JIT compile this loop since it's on a big number of iterations. JAX will unroll the loop, so it's gonna be too slow to compile. So we replace this with a for I loop. So here is the correction. As someone said on the Discord, you don't need that because actually for I loop already JIT compiles the body of the function, but okay. So what you needed to do here is to use this for I loop on a function here that is body here that you had to define yourself. It's a bit hard because it's functions and functions. And so this function will do will mimic the for loop. So here you have I, which is going to be the iterator. And you take, this is going to indicate to the for I loop what we will, which element we will take. Okay, so this is going to be one element of the X array, and then we're going to accumulate it. Here the 0 and the X shape 0, I'm not sure what it was. Okay, so 0 is the lower bound of the loop, so 0. Upper bound is going to be the length of the array, I guess. Is that it? No, sorry, it's not this one. Yes, the length of the array. The body of the function that we defined, and the initial value. So the initial value of our loop here is 0. Yes. You see, it's a bit complicated because you have to define a function that is really specific. And you have to JIT compile it. JIT compiles this function in the for I loop. Okay. We're just saying this construct because it will be useful for us in the Grace code. I don't think a JAX for I loop is faster than a Python for loop, but it's something that you need to write in order to compile Python for loops, because with JAX the compilation takes forever, so you have to replace them. All right, now for the last little exercise on JAX, I suggest you take the JAX scan here. All right, so this is a bit of the same principle, but it's accumulated sum here. Okay, well, you accumulate the results and you want to return the accumulated sum of an array. So now what you can do instead of this for loop that we use, sorry, okay, JAX-scan is here. Instead of this for loop on the elements of the array X, we can use scan to scan the function on the elements of the array. So this is a bit different than the for I loop because it also returns all the history of the computation. Yes, the for loop will return only the last value. So scan is a bit of a different construct, and we're going to use it also in the Grace code. So here we want to scan a function over all the elements of the array. So we have to replace the for loop by a scan. So you have to define a step function f here. The carry is going to be the element that you pass from iteration to iteration. And xi here is an element of the array. Yes. Okay. Try to do it yourself and then we correct in a few minutes. So take the JAX-scan.py here. So I've got a question. What is the motivation behind having loop unrolling being the default behavior? I am not sure. Yeah, I would have to check. Yes, in general, for loops in JAX, it's better to avoid them. Replace them with other stuff. Can we use lambda for the body? Body equals lambda I. I don't know actually. If you tried and it worked, I would say yes. But I don't know from the doc. I don't remember. I don't think it was specified on the doc. Stipple. For a loop, where is it? Yeah. I don't know, it's not specified. Maybe try. Yeah. Seems to work. Okay, great. Then you can. Is it typical for JAX to take up 100% of the graphics pipe after running the for loop solution, or does it take a while to run? The for loop solution should be quite fast. Are you sure you use the solution one and not the script one? Because yeah, I don't think it should. Yeah, I think it should be fast. All right. Okay, let's check this scan together, and then we can move on to the Grace code implementation. So this is going to be a bit annoying to write as well as the VMAP and the for I loop solutions, but this is the price of JAX. This is the price of the performance at JAX. So here, similar to the for I loop solution, you have to define a function here that you are going to scan over the elements of the X array. So it means you're going to execute this function on all the elements of the X array. What is specific to the scan instead of the for I loop is that the scan function returns the history also of the computation. So I think you can retrieve it here if I'm not mistaken. But in our case, we just want the last value. But then, yeah, you pass from iteration to iteration the value of the accumulated sum. Okay, so this is the solution. Maybe you don't need a jax.jit, I'm not sure. But okay, yeah. I don't know if this uses, no, maybe not. Yeah, so here you have to call jax.lax, which is a kind of a, how can I say, more lower level module in JAX. Yes, and you have to use the scan function in it. All right. Do you have some questions on these 3 exercises we saw, or it's okay? Okay, I'm gonna check the Discord and then. So the for I loop has some issues on IMG. Okay. Well, sorry about that. I don't know why. I didn't test my class on an IMG GPU, sorry. Yeah. Okay, so let's move on to the Grayscott implementation. So normally we should have started last week to write it, but we didn't have time. So I think we're going to have to go back a little bit on the CPU tutorial. Yeah, okay. Just let me check the. All right. Okay, so I guess it's up to you. Do you prefer to see how we move from Numpy to JAX for CPU? Or do you prefer to see how we move from JAX for CPU to well, more performant JAX on GPU? Because I don't think we'll have time to tackle everything. Sorry. Yeah, okay. Is it okay if I go back to the CPU class and you open a new notebook? Okay, or is it too much trouble? Because, yeah, the CPU class doesn't really work the same as the GPU class. Okay, I know what I'm going to do. I'm going to show you how to modify the code, and then you're going to run the modified version of the code, okay? Sorry. All right. So I'm using the class that is in CPU tutorial 6 JAX implementation, okay? So this is what we should have done on last week. So first of all, but you know already because you used it, to import JAX, you have to import JAX and also jax.numpy as JNP. Okay, this will be helpful to change the NumPy arrays into JAX NumPy arrays, stuff like that, JAX arrays. Okay, so the first thing we have to do is to handle JAX arrays in our code. So here that was our init arrays JAX function. I'm going to open the solution one and we're going to see directly. If we want to use this with JAX, we want to make JAX arrays instead of NumPy arrays, okay? So here, instead of numpy.ones, we have to put jnp.ones. It means U0 and V0 are going to be JAX arrays. I guess that's kind of, yeah, and then on JAX also, Jean-Marc showed it last week. When you want to do some modification on arrays, since JAX arrays are immutable, you have to define a new array here. And then you have to use this syntax here. This is just to say that I will put some part of U0 at 0. This is what we did in the CPU class. But now for JAX, we have to define a new array in which we will store the result of setting a part of U0 at 0. So it's a bit annoying, but this is how we do in JAX because the arrays are immutable. So you cannot just change a part of the array and leave it like that. All right, so here we have our two arrays that are initialized. Here, to reset the borders, we're going to do the same thing. Instead of just saying with Numpy, for example, I want to set the borders to 0 just with the indexation and then equals 0, then we have to do this here. So we'd have to take the, here I guess is the first row, all the columns and set them to 0. Okay? And then we can JIT also this because we have a few operations, so why not JIT it? Then this was our Laplacian. So if you remember, we wrote it last week. Here what you have to change in the Laplacian to make it work with JAX is here also the JAX Numpy instead of Numpy. Okay, so to have a JAX array. And the Laplacian, before we were using indexing and setting some indexes to a certain value. So now we have to specify the return value. We have to access some part of the array and then set them. Well, here we add them. Yes. So it's just the JAX equivalent of, I'm going to show you the old code. Where is it? Solution tutorial. Yep. So yeah, so this was our old syntax in Numpy. It worked in Numpy very well. Plus equal, so we increment this. And so in JAX, we cannot do that. We have to store the result and, oops. Yes, store the result, and then we access some part of the array with add, and we do some computation with add. All right? So this is just the equivalent, but in JAX. This is very important. When you want to time a function with JAX, you have to use the dedicated JAX function that is block until ready. So this is when you compute on the GPU, for example, the GPU will do some computation asynchronously. So if you just time with the time module without putting this, then you will have a time that is wrong. If you specify block until ready, it will mean, okay, until my GPU isn't done computing, don't give me the time. And just give it to me when the whole computation is done, even on the GPU. So here, when you want to use time it, like we did last week, on a function, you have to block it. So actually, you block the return arrays here. Okay, you have to block until ready so that you have the correct time. Okay, this we're not going to tackle. It's not important. All right, so here is an example of a Laplacian that we use with the JAX code because it's faster than the Numpy one. Even if the Laplacian with Numpy we modified it to handle JAX arrays, etc. Now, with JAX, it's also going to be faster to completely unroll the Laplacian, to completely remove the for loops that we had. If I can show you this was our old Laplacian. So we had two for loops, one on the rows of the stencil and one on the columns of the stencil. So now what we do is we unroll these loops, okay? And then this is what is going to give us the most performance for JAX. So you don't have to write it, it's already written. I think we did kind of the same thing. Maybe number, no. All right. So how do we simulate the gray Scott reaction with JAX? So here in our, I'm gonna show you the tutorial. No, GPU. So we already have Laplace init arrays that is Jaxified. Here we have the reset borders, we have the Laplacian. Okay, so now what you're going to do, is you're going to follow the tutorial to fill the rest of the functions. To modify the rest of the functions to be able to JIT compile the functions that you want with JAX and run the computation with JAX. So, yeah, this is the end of the CPU part, and we're going to move to the GPU part real quick. Oops, sorry. Okay, so the Gray Scott code that I just showed you with some modification about JAX is in GPU Gray Scott JAX.py. Okay, so this just contains what you have to fill now. And so you have to modify stuff yourself. Here you have the XLA flags that you can add to compute on GPU, as I showed at the very beginning. This function is already written in JAX for you. You don't have to change it. This function also, we just saw it. This function is the one we're going to use to compute the Laplacian. It's already made. And now what you have to do is the rest, and it's going to be a bit hard. But you have to use the construct that you already saw, so vmap, scan, and for iLoop. Okay? The tutorial to explain to you how to do it is still here. And so it's here. Okay. So you just have to follow this tutorial here. It's gonna be a bit hard, I'm not gonna lie, but you already saw the basic constructs that we're going to use, so you have your chances to do it. Okay, so try to follow all this. So the tutorial Gray Scott on GPU with JAX part, with the Gray Scott script that is in the script GPU script directory. Okay, and then you're going to have to fill all this. All right, I suggest that I take a few minutes to answer to the questions, and yes, get started with this because it's going to take a while to write it. All right. Are there some questions? No. Okay. I think there is no questions on the Discord. All right. Okay, so I suggest you spend the 10 minutes remaining until the break working on it, and then I'll just move between people to see if there are some questions, and if you have some, also ask on the Discord if you need. let's discuss about this a little bit, and then we will resume after the break on it. So the first step to modify our Grayscale JAX code is to write some XLA optimization flags. So I think I only used one in my solution. Well, you can test various ones, but for me, I just chose the one that had some latencies, I guess. Here, okay. Oh, I lost my tutorial. Shoot, sorry. So that was the first step. And now we're going to tackle the core of the problem, which is the for loops that are inside our Grayscale simulate function. So if you remember, we had a function that was called Grayscale dsteps, I think, that computed the Grayscale simulation dsteps times. And then we had a function simulate Grayscale that applied this function Grayscale dsteps on some images, or to create some images, and this we did like 1,000 times to have 1,000 images. So we have two big for loops here that we have to eliminate with JAX. So the one on the dsteps and the one on the images. Okay. So first, what you can do is replace the one on the images. So it's the outer loop. And for this, you can use jax.lax.scan. This will scan your function that computes V over all the images that are contained in images arrays. And you will also carry the state of V for the next image, because this is important. We want to scan our function over all the images, but the second image is going to be computed with the result of the first image. So for this, you have to follow this instruction. So you have to define a function that is called simulate dsteps. So it's going to be a bit equivalent of our Grayscale dsteps function that we used in the CPU class. But we're going to have to modify it to be in accordance with the JAX requirements. So according to the jax.lax.scan doc, it has to be a Python function that accepts two arguments, where the first is the value of the loop carry and the second is a slice of the array images. So the only input argument we need in our case is loop carry, so what we are going to carry from one iteration of the loop to the other. And we're going to return a pair where the first element represents the new value for the loop carry and the second represents a slice of the output. All right, so this you have to do it yourself. So you're going to keep for the moment the for loop over the number of steps, but you're going to modify the simulate chunk function to add this simulate dsteps function inside. And then scan this simulate dsteps function over inside the simulate chunk function over the images array. Okay, so you're going to scan your Grayscale reaction over all the functions of your array, but you're going to pass the result from one image to the other. All right, it's a bit tricky to do. We're going to see the solution after the break. So I think the break is like half an hour. Yes, okay. All right, so try to follow the doc that you have here, the arguments, the return arguments. Fill the parts that are here commented. And this one-step function, you're going to do it in the next step when you replace the for I loop over dsteps. All right, good luck, and then we'll see us after the break in half an hour at 4. See you. Okay, welcome back. We're going to finish the JAX tutorial in the next 30 minutes, I guess. And then Jean-Marc will present packaging and binding in Python. Okay, so we were on this part of the tutorial. You had to scan the simulation over all the images. So you had to replace the for loop over the images by a scan construct. The next step will be to replace the inner for loop over these steps and replace it with the JAX for I loop so that we can JIT compile the whole code. So you have the instructions to define the for I loop. So you're going to have nested functions because you're going to have this function here that you're going to JIT compile. That will include this function here that will perform. Yes, that will include this function that will perform the for I loop. Yeah, you will apply the JAX for I loop over the function compute step. No, okay, there is an error over the function one step. And then you will use the scan to scan over the images. Okay, so this is the whole function that you have to modify, and then the rest you don't have to worry about it. I already changed what you need to do. Okay, so I will leave you a few more minutes to do this. It's a bit complicated. But yeah, try to do it yourself. Let me know if you have questions, and then yeah, maybe at 4:10 we can see together the solution. All right. So we have a question on the Discord. What makes JAX generally preferred over CuPy? So I guess maybe Jean-Marc would know. Jean-Marc, there is a question that is, what makes JAX generally preferred over CuPy? Well, I think JAX is mostly made for deep learning, stuff like that. Yeah. Ah, ça marche le micro?
It's a GPU and CPU without modification code. With some functionality to distribute compute. And you have also feature to compute gradient, useful for statistical stuff.
Okay, thank you. So maybe you remember from last week, but some functions are hard to JIT compile because you will have, I think, a tracer error. Because there are some arguments that you have to declare as static in order to JIT compile your function. So that was in the class of Jean-Marc last week. I also put it on the CPU class that we saw very quickly today. I can show you. Yes, so if you try to compile this griscode dsteps function with all these arguments, it will tell you that the arguments that have an integer value, like dsteps, they need to be replaced by a tracer value. And to fix this problem, you can declare these arguments as static. For this, you have to use the partial module and declare your arguments as static here. Okay, so instead of running jax.jit, you run partial on jax.jit, so it will JIT compile everything, but it will declare these steps as static. So this was an example for the static arguments, and here in our simulate chunk function, we're going to use partial over d steps and k images because both are integer. And so yes, so the module you want to use is functools.partial. All right, so be careful about it, but anyway, if you don't put it, it will tell you that there is an error, so. All right. Yeah, so the part I just explained actually corresponds to the steps 9 and 10 of the exercise. If you try to did compile it as is, you will have this tracer integer error, and so you have to make n images in this step static. All right, let's wait a few more minutes to write the code. I will go check among the people, ask questions on Discord if you have some. Okay, so I will leave you 5 more minutes to finish this. So you have to go through the, well, 4 you already did normally, but then the 5 to 10 steps, you have to go through them. And yeah, to run your code once you're finished, you do as we do usually. You go to the GPU cluster directory if you're on Rust. And then you just have to change this. So here, if you modify your script directly, you can put script here, and then you put the name of the Python file. For me, it's grayscale jax solutions, but if you modify the script directly, it's going to be grayscale jax.py. So I run this for 1,000 images. The solution that I'm going to show after, because I leave 5 minutes for you to finish. I had a simulation that lasted for 17 seconds for 1,000 images, so it's nice. It actually compares with the QPy performances and the PyTorch also that we had last year. Let's check maybe the video, because now I made one with 1,000 images. So we're going to see soon how it behaves at the borders. We did a little trick so that we would not have to worry about computing the borders. Yeah. Yeah, so our trick was to always remove the pixel on the borders when we save the images, and to set them back to 0 when we compute the other image. Okay, so we can see that it all behaves normally. So this was made with the grayscale jax solution Python file. So let's check together what it contains, which changes did I have to make to the grayscale jax.py script to actually use jax to the fullest. So remember, the first step was to scan the computation on the array of images. So for this, this is going to be these instructions here. So we have to scan the function simulate these steps over the k images that we have. And so here the return arguments, they are given to you by the doc that I put here, okay? So you just have to follow the input arguments and the output arguments when you want to write the function. So, okay, I'm going to use scan to scan my simulate these steps function over the whole array of images. So as you remember from the scan exercise, this simulate these steps has some precise requirements for us to be able to scan it over the images. So you can check the doc, but this simulate these steps here, I put here what you have to have as input array arguments and output arguments. So for input arguments, according to the JAX documentation of jax.lax.scan, you need the carry, so what you're going to pass from one iteration of the scan to another, so from one image to another. So this is going to be a tuple of our arrays, U and V. Why is it a tuple? I think it's because the carry needs to be one element. So we have to define a tuple because here we want to pass U and V. And this is a placeholder for the scan index. We don't need that because I think we're going to scan over all the images of the array. So I don't think we need that. And then we return UNV, the tuple of updated arrays, and the V array to store as image, because you remember for in the images we always plot V as what we chose. In the HDF5 file we only store V because U is kind of the negative of it. Okay, so this is the doc of the simulate dsteps function that you're going to scan over the whole array. And what does it do? This is going to be another step of the tutorial, is this step here, when we replace the inner for loop. Okay, so this simulate dsteps function, you're going to simulate Gray-Scott number of times in it, and then you're going to update the arrays U and V and return them. Okay. So this is simulate dsteps. Now inside this simulate dsteps function, we want to do the for loop over the number of steps, so 32 or 34, it depends, but let's say 32. So 32 steps between each image that we compute. And so this, remember in the our Gray-Scott implementation for CPU, it was a for loop over dsteps, where we repeat Gray-Scott dsteps time. Now we want to replace it, because if we want to jax.jit it, then we're going to have a problem, like we saw in the Python for loop example. Jax will unroll the loop, and here we have 34 steps, but so it's going to take a bit of time to compile. So we'd rather just replace it with a jax for I loop. So to do it, instead of for step in dsteps, etc., and we apply Gray-Scott, we have to define a function here that will be JIT compiled by jax when we call for I loop here, okay, on this one-step function. So it's a for I loop nested in a scan. It's a bit annoying, but it's actually the implementation I had the best performance with. So this for I loop, we know we have to create a function one step here that will apply the Gray-Scott step. It will apply it from 0 to dsteps, which is 32. Okay, 32 times it will apply it on the U and V arrays. I think that's, or maybe that is the input arguments. Yeah, that's probably it. Okay. So you have the definition here of the one step. You need the step index. Here we don't use it. Yes. And you need the, yeah, because it's, well, there is no, we don't use the index in our Gray-Scott computation. We just repeat it dstep times. And then you still need the UV tuple, so the tuple of UV arrays, and you return the updated U and V arrays, okay? And so this one step is closer to what you already know in the Gray-Scott Python code. So it applies the Gray-Scott for just one time. I don't think we changed much things here. We have to declare a JNP array, for a JAX array. We use the Laplacian unroll JAX, which is the latest Laplacian that we wrote when it's completely unrolled. So it's this one here that is the most efficient with JAX. So where was I? Okay, so this is one step, and this step here, we're going to apply it dstep times on the U and V arrays with the jax.lax.for I loop. All right? So this is basically what we have to write to do this Gray-Scott step 32 times and for 1,000 images, for example, with a scan here. All right, yeah, just here at the end, be careful that you want the tuple of arrays. And yeah, it's in the documentation here, and the V array to store as image. So when we store the arrays as images, we remove the borders. It's just our trick to not take them into account. All right? And then from one image to another, we have to reset the borders using this function. All right, so this is our final implementation. Then the simulate and save chunked, there is no modification, I think. Yes, because it's kind of a Python function, yes. So just to really point out the fact that here we want to JIT compile this function here, which is our main computation function. So we have to declare these steps and k images as static. This is the for I loop. Maybe we don't need to JIT it, but I still put it here. But maybe you can remove it. And then in the function that does all the I/O, one thing to take into account is the fact that the timing needs to be accurate. And so remember, we called block until ready to tell the time module to wait for all tasks to be completed, the event task on the GPU. So this we have to say also. So UNV are the arrays that get computed and that are the results of the computation. So when we say block until ready on UNV, it just says, okay, until these are not completely filled with all the computation, you don't tell me that the computation is over. So this will enforce a correct timing of this JAX version of the Grayscott. Here, nothing to worry about. So JAX, it's a bit like Numpy for the JIT compilation. You will have, the first time you execute your function that is JITted, you will have some time spent on the compilation. So we just removed this from the benchmark because we want to time the execution of the function and not the compilation and the execution. So I just called it once here. This is my function that is going to be JIT compiled. So this is going to take a while to compile. So I put it before the benchmark. Yeah, one thing to be very careful about is this, the stencil. We have to convert it to a JAX array. It's not just a Numpy array. It has to be a JAX array for that, so we can make all the computations with it. So I call this simulate chunk function. This is going to produce a compilation of this function that takes into account the argument types and the argument value. So if we reuse it afterwards, we will use the compiled version and it's going to be much faster. We don't need to compile beforehand, simulate and save chunk because it's not JIT compiled. In fact, if you try to JIT compile it, you will have some problems because it uses external libraries such as H5Py and stuff like that. So you will not be able to JIT compile it. Okay, so we JIT compile. We start the benchmark, we initialize the arrays, the JAX arrays, we simulate our whole Grayscott function, and that's all, and we make the video. So here in the benchmark, of course, we have introduced this here so that we time the right time. Yes, there is a question?
Yes. Why is it not able to JIT compile? Like you just, it's just dynamic linking, right?
It's just what?
Dynamic linking. Like, even though it's an external library, it should be able to link during runtime now.
Oh, really?
I don't know how it works in Python, but in C it works.
I don't know, but I think with JAX, I'm not sure external libraries are actually supported. I know in Numpy it works, but I wouldn't say all of the libraries work.
Okay, thank you.
Yeah. And I guess you're going to have other problems. I don't think it's a good function to JIT compile because you have a lot of I/O that is done. You have this, and this that you have to make static. So it's going to be a bit hard. You can try maybe it will work, but I'm not sure it will be faster. I think I already tried and it didn't work. All right. So are there other questions on this JAX implementation? Did you manage to write the functions? The scan, the for I loop? Maybe it was a bit hard. It doesn't work? Okay, I'll check after if you want. There's a question on Discord. Why do we declare the JNP array UVV before the multiplication UVV, and why don't you use in place U? Why do we get on V? Why do we declare the GNP array? Here. Okay. Maybe it's not needed. Here, this. I just wanted to ensure that it was the same size as U and that it was a JAX array. But maybe it's automatic when you feed an array with the product of other arrays. I also wanted to ensure that it was in the right data type. So zeros like will use NP float 32 because U is NP float 32. So maybe also that was why I declared it like that. Because if you just do this line, I'm not sure your array will be float 32 here. Okay. Why don't we use in place U plus equal? I think I'm not sure we could in place U plus equal. The thing is you have to be careful about the fact that JAX arrays are immutable. So U plus equal, I'm not sure it would work. And the last question was, why don't we get on V? Why don't we run get on V? I don't know where you want to use that. Why do we use get on V? Yes, it's because here we're doing an indexing. Okay, so JAX to access the elements of an array. If you do just V and the indices, it can sometimes it will not work because JAX arrays are immutable. So sometimes I think maybe if you were to get the whole array, it would work. But here we're just taking the array without the borders. So we have to access it with @ and then do get to get the elements that are at these indexes. Okay. Here the solution doesn't use jax.lax.add like we did it in cunumeric.add. Any specific reason to not use it? No, I don't think there is a specific reason. I think I just didn't put it, but I think it should work. Yes. All right. Other questions? Okay, so I think that's all for the JAX class. Thank you. And then Jean-Marc will continue with his class on binding and packaging for Python. Okay, thank you. Hop là.
So I'm going to talk about you package and binding. So the course is in a dedicated package available here. And so the course is in the README. So I create a package example with an arborescence for source, text, test, binding, etc. So I describe this package and use a tool step by step. So overview. So this repository is a particle template for building a Python package with C++ extension powered by Nanovide. He demonstrated how to organize a Python package using the SRC layout, configure packaging and native build with pproject forms and CKit build core. Manage dependency and developer workflow with Pixie, and structure test in unit integration end-to-end. Use Roof to linting and formatting, and expose C++ code to Python with Nanovide. So the goal of the package is to be a starting point for a hybrid Python C++ package, where you need to have a clean project structure, reproducible environment, native extension build through a CMake, and testing and code quality foundation. So the project following the SRC layout, where compatible Python code live in SRC bind template. So as we can see, the name of the Python library is the same name as the package. It's a good practice to choose the same name. So you have SRC directory with Python code and C++ code, and the test is outside of this. So why this LAOC is useful? It keeps Python and C++ sources clearly separated, and they keep test and source also separated. Pixie is a dependency manager. It's a packet manager that simplifies dependency management for different development scenarios. Pixie terms, it's a file definition, configuration, define dependency and one workflow commands using feature and environments. Why use Pixie environments? Isolation, it keeps development tools separate from production time dependency. This avoid bloating your installed package with unnecessary build tooling. Reproducibility, the Pixie log file binds all transmittive dependency to exact version. So every team members, like CI pipeline and so on, gets identical environments. Workflow automatization define name task in Pixie pointers and run them in the correct environment context. No need to remember complex shell command chains. And multi-use cases switch between environments for different works without reinstalling. So features and environments. So Pixie pointers organize dependency as features, then combine them into name environment. Feature defined in this project is a runtime with the main package, Python, Nanobyte, Numpy, CPy, and so on. Another feature is only for test with package PyTest, and another feature for quality code, lint, static analyzer with package roof. For me, I cannot install CMake with Pixie. I have 5 system issues. Pixie can use a very long name, and my system is too old to Pixie. So if you don't have CMake installed, you can try to do it with Pixie add CMake, or you use the system installation. So you can define a feature in Pixie pointers like this. Features, the name of the Okay, features. So the test features is defined like this, with Pixie add the name of the features and the name of the package. You have also this one, and the runtime is here. To define your feature, it's command Pixie add. I don't have example, but it's I forget it. So it's like this one. Pixie add is the name of the package. And if you want to create a new feature, say pixie add -f is the name of the package. After definition, after feature definition, you can combine it and define environment. So the default environment is a runtime with the main package like Python and Numpy and so on. And for example, I define a quality environment with the runtime and the feature test with a PyTest and a lint feature with a roof for formatting, static analysis, and so on. Oops. So the usage pattern, it's a daily development. You can jump into your environment with a Pixie shell. It's like Condor activate my environment for Condor. And in this environment, you can install your package. You can also use it for testing a code review. You can directly install the package in an environment with Pixie run. So the task is defined here. So install is the task of test and run this command. And to run the PyTest, the test, you use PyTest. So with this command, the Pixie installs the environment and runs the command in the same time. So benefits summary. For solo developer, one command to switch a tooling context. For team, overboarding is trivial. Pixie shell and you are ready to code. And for CI, deterministic build with the file Pixie lock. And for user, smaller install footprint, production never includes TUFDEL. Packaging a build system. So the file pproject.terms is this one. This one. So the main functionality is a build system. Project contain metadata, and the definition of where is the sources. So the file pproject.terms define both package metadata and the native build backend. So build backend, it's a scikit build core, is necessary for nanobyte. C++ binding framework nanobyte. Here. In fact, you have both of them. And package metadata, project name, version, author, Python requirement. At the build time, scikit build core drives CMake. In my racine of the package, I have a CMake file. And the compiled shell library is installed into the Python package path. So this project is currently build the process scalar extension and install it into a bind template scalar. We will see this in detail later. So to install it, you can use pipe install. To install it in edited mode, you can install it. You can install with pipe install -ea point, and to remove it, pipe uninstall blank template. You can also distribute this package with the URL of the GitHub or the repository, Git repository, with happen Git plus in front of URL. So when you write a pipe install blah blah blah, the package is installed on your computer. Now speak about to you testing strategy. So the repository is organized around 3 test levels: unit test, validate isolate function class with for fast feedback, integration test, validate interaction between components, et end-to-end test validate complete user-facing workflow. If you are interested in software testing, you can consult the International Software Testing Qualification Board, ISTQB, and here you have course about the test, and as well the definition of term related to the software testing. For example, black box. What is a test black box? It's like a referential for the term of the testing and software engineering. Current automated example include unit test for the C++ backend process scalar class. PyTest basic use in this project. So to do test with PyTest, the test module name should use the test underscore prefix, like test underscore the name of the class. The test function names should use also a test underscore prefix. And to return the result of the test, you can use assert for exact comparison. Or for numerical domain, you can use a Numpy function, all close. We'll compare 2 arrays element by element. So here you have a test file with that can be exploited by PyTest. So you see the name of the test begin by test underscore, return a value, and here the test if two arrays are closed. You can consult PyTest doc to discover all amazing possibilities of this library. There are many possibilities. Now, code quality. ROF is a primary code quality tool for a project. It's a linter. It detects style and correctness issue. It's a formatter. Enforce your consistent code style. And you have some autofix can automatically resolve a subset of issue. And the typical command is ROF check a ROF format. Before start the nanobyte part, I propose you some exercise. So you can clone this package, please. And in this file, you have some exercise. Slow. There are two kinds of exercise, one for Pixie and one for nanobyte. Bon. I have the same on my computer. So the first exercise is to add the coverage feature with module pytest-cov in Pixie feature test. And modify the task test unit to display the coverage report at the end of the test run. So clone the package. So I will do the first installation because I don't have put the right syntax in the documentation. So we must add this package in test feature. So it's Pixie add feature test and peak of test. You can check your Pixie pointers. He add this new package in the test feature. And now to modify the task unit test to run the coverage. So you need to know the syntax. PyTest cov. So the syntax is this one. PyTest -- cov the project and the test directory. Pixit pointers. Okay, where is test unit? Is here. So I keep the V option cov. So it's the name of the library. So it's a bind template. And the test unit is here. So to see the result, you can go in the Pixie quality environment. So Pixie shell quality. Ou you can run directly the task, in fact. Run task environment quality test. So I have an error because I don't install the source in the package. So here you have the part of PyTest. I have only free test. And this part is come from PyTest coverage. So you see you have a summarize of your package, module by module, with the number of line and the number of line without test. And here you have the percentage of the coverage. For this module, it's a special case because it's not, in fact, Python code is Python from C++ binding. So actually, there are no line coverage. So try to now use the roof. If someone needs help. So roof, the roof. more Pixie. In fact, here roof is already installed. So the exercise is to add a task to format the code. So we need to modify Pixie pointers, add a task to the lint feature, and to run the format. So it's close to is up. Is this? So you put this this command in a task in lint feature. You need help? It's okay. It's okay. So in fact, the solution of the exercise was in branch. So for Pixie solution, so to add a Pixie, to add a roof to it's an error. In fact, is linked. Sorry. And the task format is like this. Pixie add lint enfin non. So I must create a new chapter, I don't know the term, lint. The name of the task is format. And I run roof format on the source package. Oops. Okay. Format. Format. Task. Ah oui, ma mistake. Task. So if three files reformatted, So you can check the result with one file, src, template, no, yes, example. So if you see the original so if you see the original file, you will see some difference. For example, this one. Okay. Exercise. Now, roof can also deal with import. If you can see, the import is quite not very clean. So is this syntax. And I will add this command to the format task. Alors, I go to the Pixie terms and the only thing you do. Tiens. Is to add this symbol. Check, look, fix. I need certainly the directory. Okay. Pixie 1 quality format. So the raw formatting is process. Source. So now you see the import was clean. First, the Python native library, and after the external import. Now you can add the check. It's a static analysis of the code with a check feature of roof. So create a task fix code. So before apply the fix, you can see for the module example, there are import not used. And certainly the roof check will detect this problem. So new task, fix code. Roof. Maybe there a task before. Format. Before fix, you have the task lint with only the warning of the code. After you will define the fix. So lint, so roof check of your code. So check. No, lint pas, excuse me. And you can see, as you can see, there are many problems, and roof copies the chunk of the code with the issue. So here the roof indicate that Numpy is not used. So now you can implement the fix. So to implement the fix, the syntax is roof check fix is the name of the directory. Fix code roof check fix yes. So now run the fix code. Okay. 7 error found, 7 fix. Good result. So, as you can see, all unused import was removed. So with one command, you can, with 2 commands, format and autofix, you can clean your code, and you can clean your code easily. Okay, it's all for Pixie. Now we we start a nanobyte. So I return to the README on the GitHub package. So nanobyte. Nanobyte allows calling C++ code from Python. So in my package, C++ implementation files are in source CPP lib. And the binding is in SRC CPP bindings. So the first thing to do is to write a CMake file. And there are 3 key points in this CMake file. First, find a nanobyte with a find package, a nanobyte, blah, blah, blah. Build your extension module. So with a nanobyte add module, here is the name of the Python module. Here you have the source of the C++ class, and here's the code of the binding with nanobyte syntax. And the last step is the installation in the library with install. So the target is a process scalar defined here. And the destination is in Python package in package scalar. When the compilation is done, you generate a chair object, .so for Linux, and then is importable from Python as a regular module. So now we will see this part of the code, the binding, is only this, because my C++ class is very short. Maybe I show you the class before. So the class to bind in Python is defined here: source CPP libs scalar CPP. So maybe the point H. So it's a class with a constructor, with 2 methods, add, with integer and parameter, and the second method is multiply with int also. So it's a very simple class. So how to bind it with nanobyte? So it's here, it's a very short too. You import nanobyte header. You import the header of the class you want to bind. And you declare modules, NB modules, nanobyte modules. You define the name of a Python modules. Here you have the doctrine, and in this module you have one class. So here you have the name of the C++ class. With string you have the name of the Python class, and The last parameters is the docstring of the class. You have one line for each method. So here's the constructor. The first method add is associated to the method add in C++ class, and multiply is the same thing. If you want to see the complete documentation of a nanobind, you can find it here. There are three levels: basic, intermediate, and advanced. And for exercise, we will see the binding of n-dimensional array used by Numpy. So now the compilation is the installation. So for the step of development and debug mode, you can directly compile your CMake file with a command CMake. So you create the roadmap for the build, and here's the build command, and if necessary, the command to clean the build, to correct your mistake and restart to 0. When each step is correctly compiled, the installation is, in fact, the compilation and the installation is performed by the pipe install. And thanks to the build system configured in the Pi project terms, CKit build core. So this build system do all the work, compile the CMake file, and install the new library in Python package. So after the minimal usage, so bind template is a root of my library. I have one package, Scala. Process Scala is a module, and is like a file, a Python file. And in this module, I import a class. So the class process Scala. So I create an object, and I can call the method add and multiply. So as you can see in test, you need Scala. You have a test for the process Scala, and it's like this. So now I ask you to bind a new class. With this template, bind, no. With this template, so it's the name of the class is process ND array, and you have one method. It's addition in place. So the first parameter is a Numpy array, and the second parameter is a scalar. So you add the scalar for all the elements of the Numpy array. without copy. The second is inspect method to see the description of the ND array in C++ part. If you want, you have the example in the NanoPy documentation. I don't know exactly where. Yes, it's you can consult the intermediate chapter paragraph and dimensional array. So you choose the array from Numpy, and the inspect method is here. You can use it for your exercise. So go to the exo Markdown file to see exactly what you must do. You have a free exercise, in fact. Solve some flag configuration. Create a new class process ND array, and add a second class in the module. You can have several classes in the same module. It's possible. Right. Discord. Je descends. Ah. Ici, là. Can we add Python static type annotation to the Python visible? The binding code, the Python syntax doesn't appear. The only thing you can put is a docstring or doc method. So you can put information of the method in the docstring of the method. But not a type annotation is not possible, I think. So as a 4-pix exercise, you have a branch ND array solution. And go to as the end. So you have the solution as an explanation. So the first exercise is to solve flag optimization issue. So to do that, in the README, indicate use some command to run a CMake. This one. And to see the whole complete line of compilation, you must add dash verbose and examine the flag of optimization used. So use this line. So so I need to go in Pixie shell to have the right environment. And now I can use CMake command. After build. With verbose. So here you see the optimization level 3. Et optimization size. The flag is row defined. In fact, if you go to your CMake file, this line, CMake build type release, activate some optimized flag compilation, like O3. And nanobyte add module add optimization size. So it's a strategy to have a little library for the binding because it's smaller to charge, to download, and so on. But if you code here is a numerical code, you need to compare with optimization level 3. So you can remove this option from nanobyte add module with add this keyword no mine size. So if I add this is not the good file. CMake. So take this keyword. Save. So I think I need to clean the build with this command. And rebuild with verbose mode. And level 3 and optimizer size disappear. So okay, for the first exercise, now you create a new module with one class that use ND-array parameters. So here you have some indication. With the right signature of the function. So try to do this. Here you have the list of the task. So first you must implement in C++ this class. You must create the binding. You must modify the CMake file to compile it and install it. And at least do the test. And perform the installation. And add a test in a unit test in the package. So Alice in me must go to the train station in 5-10 minutes. So I will done the first step solution. We will examine the implementation of the class with ND array in parameter. So I am in the ND array underscore solution branch. You have the right signature of the method. So it's NB 2 ND array. We will fix for only one type. We don't manage the casting here. So you manage only double type. And here you accept only the array with convention, C conventions contiguous instead to Fortran convention. So to have no copy, the array is a reference. So with this signature, we receive a Numpy ND array in reference without copy. And the second argument is a simple scalar. So the first thing you can do is check if the array is valid. I think this method is a method you can have in Numpy part. So you don't have information of the dimension of the array, but you can retrieve it with size. You have also the same attribute as in Python part. So you retrieve the size of the array. And you keep the dimension, and you create the loop, and you add for each element the value of the scalar with the in place feature. That's all. So in the C++ part, you have your ND array with almost the same method or attribute as in Python part. For inspect, as you can see, you have also the shape method, strike. In fact, in Python part, the shape is an attribute, and in CPU part it's a method. No, in fact, for the multi-dimensional array, he retrieves the value at the right handed. Okay, and you have also the dtype method to define the type. Okay, the exercise is not finished. You have three steps again, but you can consult the solution if you have a problem. So we will stop here. Thank you.
Okay, thank you everyone for attending the lecture today. So we'll finish a bit of time ahead of time because Jean-Marc and Alice have a train to take. So we'll compensate tomorrow. We'll be a bit late, and just to to have something balanced. So hope you enjoyed the day today. So tomorrow we'll do some magic with Fortran. And I will present you also an extension of what Jean-Marc just presented for package managing and stuff like this. But I don't want to spoil too much my presentation of tomorrow. And that being said, we can do some wizardry if you want here, just for must, not for the other. Have a great night and see you tomorrow. Bye.
Goodbye.